Thanks for joining. We're very excited that you're all here, and we have a lot of people online as well for this conference workshop on confronting Earth system model trends with observation. So I'm Isla Simpson from NCAR. This is Tiffany Shaw from University of Chicago. So we've been the kind of co-leads of this workshop, and we're going to start off with a brief introduction as to why we're having this workshop and what we hope that we'll get out of it. So I'm going to kick things off, and then I'll hand over to Tiffany for the second half. So just a few things to know. One is that we're not really supposed to have food or drinks in here, and it's fine if you brought some in without knowing that, but please make sure you take your plates and things out. No one comes in to clean the food afterwards. And then we're gonna, I think for the most part, be using these ceiling mics, which are up there. You see these green circles. When the green is there, that means they're on, and they're very effective at picking out noise. They're gonna hear everything you say online. So I advise you, don't have side conversations when those microphones are on. Apart from anything else, it'll be distracting for the people online. We do have a reporter from Science who is interested in joining because he is interested in this topic, but please continue to speak freely. You won't be quoted, or none of the talks are going to be reported on in any way unless he contacts you separately to talk about it. The posters are a very important part of this workshop. So all of the posters are going to be posted in the online gallery. For the virtual posters will have lightning talks, so you can find out what's on them, and then you can go and see them. And also, please contact the presenters if you're interested to talk to them more. And we'll have the in-person posters. We may have some chaos with that with the snow, but more on that later. So this is a CGD code of conduct that we always put up at the beginning of our meeting. So I thought we'd put that up here. We hope we'll have a lot of vibrant discussion, but please make sure that kind of stays respectful. Please provide constructive feedback and make sure everyone gets their chance to talk, especially in the breakout sessions. It's really important that we get to hear everyone's voices during those. And I also want to thank the sponsors. So we have funding from US CLIVAR, NOAA, NSF, and NASA, which has allowed us to bring the invited speakers and also give travel funding to many of the early career participants as well. And so we have 196, so I think that might have increased a little in the last 24 hours, probably close to 200 attendees, but 63% here in the room, the rest virtual. So we have a big virtual participation, and we hope that it will be as fruitful for them as it is for us in person. Lots of early career attendees, 62% of that classify themselves as students or early careers, so that's great to see. And we have participation from many places around the world. So obviously a bit skewed towards the United States, just given where we are, but many countries participating. So hopefully the time zones are not going to be too awkward for all the virtual participants. So I want to thank all of the scientific organizing committee that's listed here, as well as Alyssa and Mike from US CLIVAR, who really have made this workshop happen. And then Carrie Dawn, who's outside, who is a local organizer that's making sure everything is working smoothly on site. And then, of course, also Paul and Nick in the back there who are helping us out with all the. So just a bit of motivation. Why did we decide that we should have this workshop now? We really want to have kind of a stock take of how are our models doing in terms of historical trends compared to observations. And why we thought this was timely now is that we have a satellite-based observational record that's more than 4 decades long. And during that time, of course, the planet has been warming. So just for the speakers, this is a difficult thing to use, but it's working. Kind of. So, okay, so we've had, this is global mean temperature in observations and in models. And of course, we have been warming over the last 4 decades. So we're at the point now where the climate change signal is getting kind of big, which allows us to really start to isolate signals from noise and really be confronting our models now with observations. Also, of course, large ensembles have become a much increasingly used thing. And we had the large ensembles workshop here about 4 years ago, led by Clara. And those large ensembles really allow us to really be confronting our models with observations, because they allow us to have the perspective of the relative roles of force trends and internal variability, and how certain are we about what the trends are in the observational record, or what the force trends are. And so, of course, the IPCC does synthesize how models represent trends, but here we're hoping to go into more detail, into more processes, more variables, and more regions, because, of course, work like this feeds into IPCC reports. And models are starting to simulate more and more processes, like in CMIP7, there's probably going to be a much bigger role for emissions-driven simulation, so we're probably going to hear about that a bit later in the week. So, many more things that we start having to worry about as to whether our models are getting things right or not. So just a couple of examples to motivate us before we get started. So this is from a paper led by Rob England-Wills, but others had kind of noted this before that. But this is a nice summary of some of the issues we have with sea surface temperature trends. So on the top left is the observed sea surface temperature trend, and you can see that we've had this relative cooling here in the Eastern Tropical Pacific, a feature that you don't really see here in the multi-model mean. And then when you look at all of these large ensembles here, this is a metric of the difference in sea surface temperatures between the West Pacific and the East Pacific. And these black lines here are the observations, which have seen a strengthening of the SST gradient. And then these are all of our large ensembles. And so for many of the models, that strengthening lies outside of the model distribution, suggesting we have a problem. But for some of them, it's kind of at the edge. So this is an important feature that there was a whole workshop kind of about this a year or two ago. So this is an example of where we're starting to worry that we're not getting something pretty major right in the models. Here are a couple of other examples. So the ones on the top are jet stream and storm track trends. So this is a figure from a paper by Rei Chemke, who's one of our invited speakers. And it's showing trends in vertically integrated eddy kinetic energy in the southern hemisphere. Sorry, not trends, just time series, but you can kind of see what the trends are from that. So the gray lines are all of the different models, and then the blue is the reanalysis. And the reanalysis here is showing a bigger increase in eddy kinetic energy than what the models appear to be simulating. So I think we're going to hear more about this, maybe from Rei and also from Joonsuk later in the week. On the right here, this is maybe a more positive example. This is where the models seem to be doing something pretty right. So this is trends in the summertime Eurasian westerly jet. Black lines here are observations, and there's been a weakening of that aspect of the circulation. And then the black PDF here is all the trends you get from pre-industrial control runs. And then the blue is what historical forced simulations do. And so the forced trends seem to align very nicely with what we see in observations, and they've attributed that to aerosol forcing. The final example here down on the bottom is maybe okay, this is maybe what we mean by kind of the ugly aspect of the type of but so this is a nice example of Arctic sea ice trends. So the black PDF here is all the trends you get from the models. And then the green line is the observations. So there's been this decline in sea ice. And if you just look at this at face value, the observations are within the model distribution. So we maybe don't worry too much that there's an issue. But this paper looked into that in more detail. And here you're seeing the trend. Okay. Yeah. Maybe I could use the mouse. Yeah. And, on the y-axis here in sea ice, and then the global mean temperature on the x-axis in the models. And what you see is that the models that are able to capture a trend as big as what you see in observations are doing that with a much bigger increase in global mean temperature, suggesting they're maybe getting things right for the wrong reasons. So those are the kind of things we want to be talking about here. We want to kind of gather all the examples of this and then motivates us to look at more things that we haven't kind of looked at yet in enough detail. I'm going to hand it over to Tiffany now, who will talk about the workshop aims and objectives.
Great. It's really wonderful to see you all here. This has been 2 years in the making, plus maybe 20 inches of snow. What we really wanted to do was to get people from different communities together. The literature is growing on this topic, and pose the questions. What are we getting right? What are the models getting right? What are the models getting wrong? Maybe what we haven't looked at enough. And really identify these challenges as a community, define new research directions, not only scientific mechanism related directions, but also methodological questions, because I think this is also a big topic. And so the goal then is to bring everybody together, bring our heads together. So the agenda is set up as follows. We're going to begin with some very nice kind of plenary talks that set the stage for where we are, given by Gavin Schmidt and Clara Deser. That will lead into the topic of trends in the mean state, which is actually quite a rich topic. We'll have many talks on that. Then tomorrow, we will look at trends in variability and extremes, so very obviously related to impacts. And then this important question about what the trends are due to and what are their relationships to forced responses versus internal variability. So Friday, we'll bring it all together and talk about fully coupled Earth system processes, and then finally showcase some new applications and methodologies, which will hopefully be useful tools for us to think about how we move forward. So a really key component of this workshop is going to be the breakout discussions. This is where we'll all have a chance to contribute, and I really hope we all do so. This afternoon, you're going to get a chance to tell us about what you see are the major discrepancies in the literature. We want to know the references, the variables, and also the implication. So we'll have some time for you to fill out Post-it notes, get up and move around and collect this information. This will be the starting point for getting us into tomorrow, which will synthesize the sort of best practice protocol. I think we've all seen these comparisons in the literature. What some people elevate as a discrepancy may not be agreed on by others. And so the point here is to have some sense on what types of data sets we should be looking at, what types of metrics we should be using, potentially also what kind of language should go along with that, thinking potentially on the lines of the IPCC. And then obviously, how much do we know about the role of these effects of internal variability? So Friday, this will take us into prioritization. We'll have gathered all of this group discussion, and the expectation or hope is we'll have a real clear set of discrepancies that we'll want to tackle as a community, that we'll want to focus on mechanisms to understand why these are happening and identify these priorities for further comparison. So the philosophy here is really to bring people together across different subdisciplines. We all go to our own workshops, our own HU sessions, but this is a theme that's emerging, beyond any of our individual groups. And we want participation from everyone, virtual, online, all stages of career. So we really want to encourage everyone's voice to be heard. And the ideal situation, I think, in the breakouts is to have everyone collect their thoughts and make sure that everyone gets an opportunity to say something if they so choose. We also would encourage you to ask questions during the oral and poster sessions. This is really important. And as we all know, there's no such thing as a stupid question. Poster sessions are also very important. People have already started to put those up, and so we look forward to an actual poster session. So what are the outcomes? Well, of course, bring this all together. There'll be a lot of exchange of knowledge in terms of writing things down. There will be a report for US CLIBAR to synthesize what we've learned and potential next steps forward. We also hope as an organizing committee to write a perspective on this topic. There may be someone online whose microphone is not muted. And, depending on the particular discrepancies we agree on, if there's motivation and interest bottom up to move forward with a US CLIBAR working group, that is certainly on the table. So here's some general housekeeping. Wi-Fi you should all have access to. There's no password. Restrooms are around. There's also lactation rooms for those who need it. Also some housekeeping here. So there's breakfast, lunch, and coffee breaks. The breakfast and snacks are going to be out here. Lunch will be in the cafeteria. There'll be a little bit of information about that in terms of lining up. Gary Don will be your contact person for anything to do with the building and meals. And we have Alyssa and Mike from US Clymer that can answer questions about schedule and workshop logistics. There's going to be breakout session assignments. So in case you don't remember yours, these will be posted so you can always take a look. And for those who are on social media, you can follow us on. So here's the helpful reminder. If you want to go to have a salad, go to the left. And if you want anything else, just keep going. Okay. So the group activity had been to have a hike. That's obviously not going to happen tomorrow, but we would still like to gather socially. And so the plan, the contingency plan now is to go at 4:30 to Avanti. The address of which is live, and yeah, starting at 5:30. So even if there's snow, it's walkable, and I really hope to see you all there. Okay, weather. So when we were planning and choosing the 3 days on which to have this workshop, Isla reminded us to always roll the dice and end up with a large snow event. So here we are. Go Isla. Go Isla. Ability there. 2 years in advance. So we're in contact with the facilities and we'll just have to take it one step at a time. We have a contingency plan for going virtual. Maybe we could also try to meet up in the hotel for those that are there. We'll just have to keep you posted, and thanks for your understanding as we kind of navigate this situation. Okay, so that's all for the intro. It's our pleasure now to move into the first session. Our first plenary speaker is Gavin Schmidt.
All right, that's okay. There we go. I was going to say that was. I keep reusing slides. I apologize. What can I say? So I'm going to give an overview of the different issues that come up in this discussion because we have been having this discussion for a long time. Pretty much as long as we've had reliable trends, maybe not so reliable, but that we've had trends of climate information coming out, and we have had models to which to compare these things to. And we get ourselves into this pickle all the time when we see an apparent discrepancy, and quite often we can have a little bit of community panic until it gets resolved. And so I'd like to give some kind of historical context on how some of these discrepancies have been resolved in the past, and that might help us think about how they're going to be resolved in the future. Next. Okay, so I'm going to throw in some philosophy because I've been hanging out with philosophers recently. I make no claims to be a philosopher, but I have noted that they use a lot of footnotes. So I've put in some philosophical footnotes for you to find amusing. Okay, click. Yeah, so the first thing that we all understand is that all models are wrong, right? They are approximate, they are incomplete, they are never, the map is never the territory, right? So all models are wrong. And so that just goes without saying that when there is a discrepancy between observations and models, the models are wrong. But that doesn't tell us everything we need to know, right? Next. The point is, like, scientific realism is the concept that we think that we're doing with our science and our models. We're actually approaching truth. We're not approaching truth. We are making things that are useful, and they are not true. And so there are no scientific realists in the climate model groups, which surprises some philosophers. Next. Okay, second point, click. All observations and comparisons are also based on models, right? So there isn't a raw observation that just stands on its own. There are models that go into the observations. There are models that go into the comparisons, and click. That means it's models all the way down. Right, so everything is wrong, or has the potential to be wrong. Okay, next. Okay, now let's do some actual stuff. Okay, so we've had a lot of controversies in the modern climate change discussion, from the double ITCZ in models, the MSU cooling situation, the hiatus, cloud phase changes right now in CMIP6. Click. And there are many reasons for this, and so you can just click through this. They're all listed. Let's go. So the first one, models are wrong. Observational data is imperfect, it's noisy, and it's biased. And it often doesn't come with estimates of structural uncertainty. And so the uncertainty that we get from observational data sets is almost always insufficient to assess whether a model is appropriately being compared to that observation. And then the most important one is that comparisons are often not appropriate. We aren't comparing like with like. There are unrecognized, sometimes point of view biases from the instrument that we're talking about, particularly for something like a satellite. It doesn't see the same variable that a model predicts, right? So a satellite view of low clouds is not the same as the amount of low cloud in a model, because the satellite can't see the low cloud if it's underneath a high cloud. Right. And of course, we know that there is an irreducible effect of the chaotic dynamics of the system, which means that the specific weather path that we happen to be on is not the same as the specific weather path that any free running coupled model may be on as well. Okay, next. Another footnote. Okay, so this is actually a real thing that is recognized by the philosophical community, and it's called underdeterminacy, and it's often called Duhem-Quine underdeterminacy, and it means that when I'm comparing a model with an observation, I'm testing multiple hypotheses at the same time. I'm not just testing the physics of the model or the forcings that went into the model or the quality of the observations or the quality of the comparison. All of these things are being tested at the same time. And at any point, there can be a failure, there can be an unrecognized issue. And so you can't immediately take a model calculation, an observation, think that they're the same thing, think that they should be the same thing, and if there's a difference, declare what the solution is going to be ahead of time. Next. Okay, so click through this. We all know about the MSU cooling situation. So back in the 1990s, Spencer and Christie worked out a new way to use MSU and then AMSU and now AMSR data to put together a time series of weighted areas of the atmosphere. Everybody was very excited by this new methodology. Their own press releases, which they wrote, of course, declared that the satellite data was the best data quality possible, but there was an obvious difference in the trends seen in their lower tropospheric data than were being seen in the observed in situ surface data, which seemed contradictory, and in fact was contradictory. Next. Just click through. So the originators of the satellite data blame everybody else, like the models were wrong, the other data sets were wrong, their satellite data was never wrong, but that actually turned out not to be the case. Independent replication of those satellite products showed significant structural uncertainty in the trends of those things. Correction factors were discovered, orbital drift, errors in the diurnal correction, and all of those things as they occurred, led to reversal from that cooling into a warming. And we are now in much better concordance with the model. So the upper figure is the comparison of the CMIP6 models for the lower troposphere compared to 3 different estimates of the lower troposphere trends, one of which is very firmly within the scope of the models. The other 2 are slightly cooler, but the point is that we don't yet have a true estimate of the structural uncertainty associated with those lower tropospheric trends. We also don't really have a good estimate of the structural uncertainty associated with the models. And we wrote a paper at the end of last year or the beginning of last year, that really did a much deeper dive into that, looking at how these things change as a function of the quality of the stratospheric circulation, where the tropopause is, and what the different forcings are with respect to ozone, and found that actually the spread in the models is actually larger than the traditional estimates that we're getting from the CMIP ensemble, because we're not really looking at the whole structural uncertainty that matters for these calculations. Next. Some of you will remember the hiatus, and some of you remember like how that kind of came around, click through, starting from about 2006. Oh, too far. Go back. Oh, that's right. Oh, yeah, I put it. Yeah, I should remember what my thing is. Okay, so people would remember back in 2006, people said that global warming had stopped, and the climate science community said, no, this is a short-term trend. It's just in the noise. We're not going to pay any attention to it. And so it was what's described as a tolerable discrepancy, something that isn't quite what you expect, but in fact, we're not going to worry too much about it because it's explainable away, right? So click. Yeah. And so it's something that happens whenever there's a good theory or an efficient theory that gets confronted with the complexity of the real world. The real world is always complex, and there are always going to be discrepancies. And then we decide, kind of using our own heuristics, whether a discrepancy is tolerable or not. And back in 2006, the discrepancy between the trends and the temperatures and the models was a tolerable discrepancy, and so it was ignored by most of the climate science community. Next. Next. Yeah. But by 2012, two data sets, the HAD CRU T3 and the NOAA Global Temp version 3, the short-term trends started to approach what you might consider a 2 sigma anomaly. Next. And 2 sigma is a kind of a trigger for scientists to kind of start to get interested. And over the next 2 years, something like 50 papers started to explore why this anomaly had occurred, and everybody had their own theories for what actually happened. Next. They came up with lots of different things: forcings, biases in the observations, insufficient model variability, improvements in the comparisons, et cetera, Next. But then in 2015 and 2016, all of that talk basically just evaporated because, click, for the 3rd year in a row, 2016 set a heat record. And so everybody stopped basically talking about the hiatus. And if you go back to the records now, it doesn't look like anything because of the updates in the records, the updates in the models, the updates in the forcings, and all of those things have made that 2 sigma anomaly that was there apparently basically just disappear. Next. Okay, next. Yeah, click through this stuff. Yes, yeah. Okay, yeah, just go. Quick prediction there that by 2025, everybody will be telling us that global warming has stopped in 2024. But we will see. Next. Okay, so we know that CMIP6 has produced some surprises. This is a graph I made for real climate. There's still a lot of models that have climate sensitivities that are within the very likely range from AR6 and from the Schurer et al. Paper that we were part of. But there's a whole bunch of models, and some of them very good models, including CESM2, that have climate sensitivities that were outside the range of what people considered to be sensible. Okay, next. And you can see the impact of that on the trends. This is the difference between the screened models and the full model spread. And so the pink is the models have been screened by their TCR, so TCR within the likely range from IPCC. And you can see that that is a pretty good prediction of what the temperatures have been in the last few years. Next. But if you're only using one single run from a model, because you just want to do a good estimate of the structural uncertainty without having to be biased against different groups that have different numbers of models in the ensemble, it doesn't tell you very much about the consistency of any individual model, because you're not sampling sufficiently the internal variability of every single model. And so this is a picture of the temperature changes from the last 10 years to 30 years previously. The ERA estimate is there, and you can see that models generally that have lower ECSs are closer to the observational trend, but you can't use a calculation like this to determine whether any model is or is not consistent with that trend, because the next thing, click, which is if you use all of the runs from different models, what you find is that the observations are actually consistent with a much larger number of models than you would have got just from taking that first ensemble member. And so while you have a good estimate of the total multi-model ensemble spread by sampling one model run from each model, it doesn't tell you about how any of the individual models are or are not consistent with the observation. Next. This is a calculation that comes from work from Ben Center. It's just like a little statistical test that you can apply that essentially says what's the likelihood that the observations are consistent with the ensemble that you have taken from the models, and you can treat it like a t-test. And so you can actually quantify the degree to which models are or are not consistent with the observations. Next. Okay, so you mentioned this one earlier, Isla. This is the Southern Ocean SST trends and the differences between the multi-model mean and the observations. I can't explain the tropical Pacific, which I think other people will talk about here. But I think one of the key things for the Southern Ocean is the missing physics in the models, which is associated with the runoff of anomalous freshwater from Antarctica, because there has been quite a lot of freshwater that has come off the continent, both from losses of the ice sheet and from the ice shelves themselves. And click, if you look at some of the recent papers that we just published, that amount of water in the historical period with the historical forcings is in fact sufficient to cool the Southern Ocean quite significantly, but also reverse the trend in sea ice, which has also been an anomalous trend. And so that's an example where there was something missing in the models. The models were incomplete, and then adding in that extra factor allows us to have a better match to the observations. Next. And I think this is the last example that I have. The Earth's energy imbalance is something that is of great importance for a lot of different things, and for our understanding of how the Earth is changing and why the Earth's climate is changing. And one of the interesting things about the long-term trend that we now have from the series data, I think you can click, is that the balance between shortwave and longwave changes is quite different from, in this case here, this is a selection of GISS model runs. The broader ensemble has a bigger spread, of course, but we really looked into the differences between the shortwave trends and the longwave trends. And while all of the models approach the correct net imbalance, that's the dotted line going through the middle, they all seem to have a smaller change in the shortwave than the series data suggests. Click through. I think there's a couple more text things there. The thing to note here is that the observational uncertainty is rather poorly characterized. The uncertainty in the series data should in fact be an oval, because there is a correlation between the errors in the shortwave and the longwave because of the way it's calculated, but we don't know what that is. So I don't know what the true uncertainty oval should be for the series data, and our comparisons are are imperfect because, you know, we're looking at AMIP runs here that only went to 2014. We haven't yet had the aerosol emission that would allow us to go up to the present day. Those are imminent, I am told. But anyway, we only have aerosol emissions to 2019. We have we have quite significant differences in the SST fields. The SST fields that the AMIT runs used are now out of date. The world has in fact warmed more, we think, and there's actually important structural uncertainty in the SST trends themselves. And I think we'll see some more evidence of that as well. And so click through. So we've set up a new project. It's called Series MIP, where we're trying to drill down into this. We're trying to make those comparisons more appropriate. We're trying to make sure that we're comparing like with like, and we're trying to do a better job of understanding both the structural uncertainty in the models and the structural uncertainty in the observations, with the goal to kind of pin down this discrepancy. And I don't know how this one is going to work out, but hopefully within a year or so we'll be able to tell you. Next. Okay, so just to recap, and this is going to go through, I think, everything that we're doing in this workshop. Yes, the models are wrong, but yes, observational data are imperfect. They are noisy, they are biased, and we often don't know how noisy or how biased they are. A lot of comparisons are not appropriate because of the different points of view that the observations have and the models produce. We have to build in observational forward models to be able to match particularly remote sensing quantities that we do. And of course, we have to worry about the internal variability. And I think all of these things are going to be writ large throughout the talks that we're going to have going forward. Next. And I think this is the last philosophical footnote. You can't know ahead of time which hypothesis you're going to challenge with any discrepancy, right? You have to do the work. We have to do the work. You know, people that jump to conclusions based on one data set or one observation and declare that all modeling needs to go back to basics, generally speaking, that is not how these things have actually been resolved. And so I think that was the end. Next. Yeah. Oh, like I was just putting this together, and rather incredibly, in the last year, we've published 6 papers that talk about the discrepancies in trends between climate models and the real world, which I did not realize that we were doing this, but for all those things that I was talking about, almost all of it is there in these very recent papers, and I think you're going to hear from Lettie a little bit later on, and I'm sure you're going to hear more about MSU temperature trends from Stephen a little bit later on as well. And so thank you very much.
For a great talk. We're going to take the questions at the end after Clara's talk. So keep all your questions in mind because we have plenty of time for discussion at that point. So we'll move on to our next plenary speaker. It's Clara talking about challenges in varying models and observations on a regional scale.
Thank you so much to Isla and Tiffany and all the organizers. This is a huge amount of work and it is well spent, and I'm so glad that this community is coming together over this topic. And thank you to Clygar and thank you for inviting me to talk. So I'm going to give another big picture talk, a bit like Gavin, but I'm going to focus on regional scales rather than global mean quantities. And I'm going to raise questions. I'm not going to answer things, but I think these are, in my mind, some really first order challenges that we still have with us on comparing observed and model simulated trends on these regional scales. Doesn't seem to like that advancing.
Maybe it's like if you click on this slide.
Yep. Okay. And so it goes without saying that we need to assess the degree of model realism to put forward credible predictions and projections, and to help us understand the observed trends. So it goes without saying how important this workshop is. So in the old days, and I'm part of the old days. In the old days, we would do things like this when we compared observations and models. So this is a 50-year trend in air temperature over North America from the Berkeley Earth data set. Doesn't matter too much which data set you use. Beautiful polar amplified warming, very consistent with our, fundamental thinking of the controls on temperature over this kind of time horizon. Here's a model simulation, happens to be CSM1, and this is what it shows. And in the old days, one would say that there's obvious model and or forcing error. These are, you don't need to do statistical tests. These are really very different in their pattern and sign and amplitude. But this is not the old days, and we've learned so much from having, of course, multiple realizations of historical climate from different models. So another simulation of the same model, and it's pretty much spot on. But of course, the important thing to recognize is that each one of these maps contains a roll of the dice of the internal variability on this kind of 50-year trend timescale. You couldn't predict this outcome over that timescale. Plus, of course, the anthropogenic and natural radiative forcings on the climate system. So I'd like to address in this talk some of these high-level big picture points. So we need to really confront our models. Is the range of outcomes in a given model plausible? So how are we going to address that question? Secondly, given that we only have a single observed outcome, how can we even evaluate whether the model's ranges are plausible? And then third, I always like to step back from the model world to the observations and then look at the observations a little differently and say, well, what could another reality have been possible? Could another outcome consistent with the observed internal variability, could it have given us a different spatial pattern of temperature trends over a 50-year time scale? So going to try to give, just summarize some new approaches that we've had recently and continued challenges. This is by no means, any of this is not answered at this point. So first, is the model range of trends plausible? So this requires, of course, you have to break it apart into the force component and the internal component to address this properly. So with large ensembles or so-called single model initial condition large ensembles, SMILES, if you have enough members, we can do this in a straightforward manner by computing the ensemble average at any given time step to compute the models for forced response. And then for any individual member, you remove that forced response to get the internal component of the trend. So observations, how do we obtain the forced response? That is absolutely ongoing challenge, many methods, statistical and dynamical, sophisticated, simple, first principles, physical thinking, and AI approaches, all kinds of approaches. We had recently a workshop here at NCAR and at ETH in Zurich called the ForceSmith workshop and hackathon. And we were really trying to now in a coordinated framework compare existing methods and also develop new ones using these SMILES as a test bed. And I'm going to show you at the very end of my talk. You will have to wait to see how well some of these methods work. And the important piece for me was to do this double-blind test on the methods. The participants did not know the real answer, and only I and Adam Phillips knew the real answer because we chose. And I forget why it was double-blind. Can't remember right now. Oh yeah, they didn't know which model they were looking at. That's right. Because we took that information off. Okay, so I'm going to get to that at the end of the talk. So assuming we can do a good job with these different methods to get the forced response, then of course we can obtain the internal component of the observed trend residual. A very important point here, and Gavin made that as well, is that that is limited to one realization. So we really don't know where the observed trend lies relative to the distribution of possibilities. There could have been a different roll of the dice of the internal variability in the real world, and that would have put us in a different place in the distribution. So I think sometimes it's a fallacy. One thinks the observed is sitting, the observed map of trends is sitting in the middle of its distribution. We do not know that. It's sitting somewhere, but we don't know where it's sitting. So I'm going to make a couple points on that. So how should we evaluate model trends given this single observed outcome? So I want to highlight this. I think that's something we should really work on as a community. So first, of course, one determines whether the observed trend, and you can do it in a map format or a time series, lies within the spread of a given smile. But of course, this could be for the wrong reason. There could be too much spread, too large internal variability in a model. And then relatedly, and we hear a lot about this lately, the forced response and thus the associated signal to noise ratio might be too low in models. So this is something that we really have to continue to confront in order to do proper evaluation of our model trends. So how do we evaluate ensemble spread of trends in a smile? So we need to construct plausible alternative outcomes for observations. If you only have one, it's going to be really hard to evaluate the ensemble spread of trends. So constructing plausible alternative realities. I really think this is important for all of us to work on. There are some very nice prototypes here, or more than prototypes, well established. So early on, Dave Thompson and colleagues did a very nice study where you can actually get at the you can get at the spread of trends at any length just by knowing the amplitude and autocorrelation properties of the interannual variability. And then you can scale that to show what the range of uncertainty on a trend at any length analytically would be. But this was done in a pointwise fashion, so it doesn't give us any sense of the range of outcomes in terms of spatial patterns, which I think is also a very important aspect. So you need to step into the world of the more complicated world where we know we have these modes of internal variability, these dominant spatial patterns in our climate system. So Karen McKinnon, when started this work as a postdoc here, dubbed the observational launch ensemble, where, and we'll hear more from her, I'm sure, about this. But to do is to take the long observational record, roughly 100 years, do regressions onto these leading modes of variability, and shuffle their phases because they could have, happened in a different phasing. And then take the residuals from those regressions and then do some kind of block bootstrapping to then shuffle the residual internal variability. So that was how she approached getting these different outcomes for the observed spatial patterns of trends from the observational record. But of course, preliminary step is that you have to assume some knowledge of the forced response. In this case, she used the simple method of regressing onto the ensemble mean global mean time series from a SMILE, but that is not necessarily, as we found out in enforcement, really the best thing to do. So there's a lot more work to do here. I don't think it negates the results, but this was, a first really good step. So let me just show you, come back to this North American example from her observational large ensemble. She's now, you can make any number of synthetic realizations based on this method, based on the observations. So this is from the 1,000-member observational large ensemble and centering the internal component of trends on the force component from the CSM1 SMILE. You can center it on anything you want, but in this case, that's what was done. And here we're just showing you what that range of plausible trends looks like from just reshuffling the observational data, the internal component. And again, there is a wide spread, and this range is very similar to that in the CSM1 SMILE, which we had at the time. And these are just 6 of these of the members of the 40 members of the SMILE, and just showing you, obvious resemblance. So the model spread is not out to lunch if this observational large ensemble methodology is credible. And we've tested the methodology using the SMILE and find that the errors are for this region below 10%. So I think this does show that this is a very viable approach to assessing the spread of trends in models. I'd like to also speak to show an example, not from the statistical side, but from the dynamical side. This is from a whole line of work of Matt Newman and others. I'm going to take a few more minutes. I think I started late. Thank you. So this is the dynamical linear inverse modeling. So we're not looking at just empirical statistical regressions. We are using the dynamics of sea surface height and sea surface temperature in the observations and using dynamics to get different outcomes. So with this method, you can attempt to get an estimate of the force response. This would be the gravest or first 2 gravest least damp modes. And then the rest of the modes you would interpret as internal variability. So I'm just going to show you now this example for sea surface temperature. I really like it. Again, you can make as many realizations as you want. It's all based on observations. And here are 2 of these are trends from 1980 to 2017. So again, nearly a 40-year trend here, and very different outcomes. And this is all based on the observations and the linear inverse model. So it's not based on complicated climate models. Here's the actual. We've seen this rendition before. And I've put the actual, I haven't centered it on purpose because we do not know where, right? If we put it in the center, then we would say, okay, it's forced. But we don't know that it's all forced. So I've offset it. And again, that's something for this community to really address where that, the force component lies relative to the possibility of that. So I want to use, may I go a little bit? Yeah, okay, we have lots of time for discussion. Thank you very much. So I really want to bring to the forefront here the role of atmospheric circulation because I think we have to grapple with our climate models. Do they have the right level of internal variability of large-scale atmospheric circulation trends? I think it's a really important aspect of confronting our models and having, physical insight into their spread. So I'm going to show a recent example just from one of my papers, but just to highlight the idea here. So this is the CSM2 large ensemble. Now we're looking at wintertime precipitation trends over, obviously, the European region. This is from 1962 to 2021. So simply taking, at the time, the last 60 years, I guess. So these are trends. And the ensemble mean is shown in the middle. So that is the 50 or 100 member, I forget, ensemble mean. So it's a really good estimate of the model's force response. It shows wetting in most of the northern part of the domain and some drying in the Mediterranean. And the sea level pressure is shown in contours, and there's only one contour, and that is the zero contour. So there's really nothing forced in the atmospheric circulation in this model and in just about every model looked at for this time period. And then I'm showing you a couple of N members. These are not the most extremes. They're within the 5th to 95th percentile range. So it's the plausible range of outcomes due to internal variability. And you can see that the two N members have nearly equal and opposite sea level pressure trends. And those are, of course, all internal because there is nothing that is forced. And that sea level pressure trend is really imprinting on the precipitation patterns. When you have low pressure, you have enhanced, increased precipitation. When you have high pressure, you have enhanced drying. So it's really at the root cause of these possible outcomes for historical trends. So then we asked ourselves, well, can we use the fact that there's not much of a force trend in the atmospheric circulation? Can we use this fact to estimate the force component of observed precipitation trends? And this is using a procedure dubbed dynamical adjustment. I would say Mike Wallace, Jim Hurl, they were kind of pioneers of this technique some decades ago. And the idea here is that you empirically estimate how atmospheric circulation anomalies, how they might impact precipitation, temperature, whatever you're interested in. And here we use, and then you remove that from the data to get an estimate of then the thermodynamic residual. So here we used a procedure based on constructed circulation analogs. It doesn't matter the details too much, but the idea is we're using the statistical relationships of the observed interannual variability between sea level pressure and precipitation. We're not using any knowledge of the trends. So then we get this empirical relationships between sea level pressure patterns and precipitation, remove them from the data, and then find those left. So I'm going to show you, so here's the observed trend. This is GPCC data, and I think it was the, I forget, the ERA5 sea level pressure. Doesn't matter too much. And that's what the real world gave us, but what could the real world have given us? That's the point. So here is the circulation-induced component removed. So we have estimated that dynamical contribution. You can see a lot of contours in the sea level pressure field. We remove their impact empirically through this dynamical adjustment procedure. So there are no contours by definition in that map. And that's what we obtain as this thermodynamic residual. It doesn't look identical I would never expect that it would look identical, but the point is that the amplitude is relatively similar to the CSM large ensemble force response, and maybe there's some hint of a little more wetting in the north, a little more drying in the west, but certainly there's much more, fine scale structure in the observations. So now the fun part comes with adding Aaron McKinnon's observational large ensemble internal component of trends to this purely observationally estimated force trend. So that was a step I had always wanted to go to. So here we're adding a plausible member on the wet side for the southern part of Europe here. So this is, again, based on observations. And you can see, roughly speaking, the model is not out to lunch. And here's a dry end member from the observational large ensemble. So here is kind of a really pure way of confronting models, force trend and spread of trends. The top is all based on the CSM2 model. The bottom is all based on observations. And my question, of course, this all is predicated on this assumption: is the observed sea level pressure trend for this example, is it unforced? Models suggest it is. Are models correct in that? You know, there's a lot of debate, I would say, and I'm sure we'll have a discussion on it. But that is, I think, a really key question for this community. So additional challenges, I don't have time really to show, I think, examples, but the presence of force trends may corrupt our empirical definitions of modes of variability as these force trends really accelerate, and we really have to confront that. I've done some my own work on AOV, but ENSO as well. The limited length of the instrumental record, and I'm going beyond the satellite record, 100 years of data, it really restricts our knowledge of what the true range of internal variability is. And it's just something we have to live with, obviously, but we have to be very cognizant of it. I do want to make the point that I'm happy to show an example if somebody asked in the discussion, but these ongoing SST trends of the strengthening of the east-west gradient in the tropical Pacific, it looks like it really has affected the teleconnections from this year's El Nino. So this year's El Nino teleconnections and climate impacts look different because of the presence of this trend in the tropical Pacific. And so work with Steve Yeager on that, an example. And then a cautionary note, you know, we compare models, CMIP5 and CMIP6 models. I guess I'll skip the SST trend, but I'll just get to the, should I skip the SST trend or should I, do you have a few minutes for me? Skip? No, go for it. Okay, all right. All right, so this is from, just in a nutshell, why we need to pay attention to trends and why we need to understand them, not just for their own sake, but because they are actually affecting how, you know, the climate impacts from, say, El Nino or even other extreme events. So here is taking predictions of SST anomalies for this winter, DJF of this winter, from the initialized decadal prediction set of CESM2. And they're very skillful. This is from a November 1st start date. And we put those those SST predictions on top of the observed SST trend. So that's what you're seeing in that upper left map. That's the prediction for this winter. It is verified extremely well, within a couple of tenths of a degree for NINA 3.4. Then we take that and put it into in AMIP mode to the atmospheric model. And then you see a 50-member ensemble. You see the precipitation response, and then you see the sea level pressure response in the North Pacific. That does not look like an ENSO response. I was shocked to see that. Where is the deepening of the Aleutian low? So it turns out that if you then play games with the AMIP atmospheric model and don't apply the observed SST trend, you get that canonical deepening of the Aleutian low, nothing, you know, that we didn't expect. So the point is that the presence of that SST trend, according to the NCAR atmospheric model, actually produces this high pressure over the North Pacific, which completely distorts the teleconnection from this winter's El Nino. Doesn't mean the real world has to look like this, but this is what this model says. So I think that's one reason to pay attention, obviously, to trends. I'm going to skip the probability. I'll go to this last point here, cautionary note, because some people may not be aware. When you compare CMIP5 and CMIP6 models, it's not just models are different, the forcing is different. So here is an example from a paper led by Sarah Kang. These were trends from 1979 to 2013. It doesn't matter too much what the time period is. This is the 40-member CSM1 SMILE forced response. The middle is the CSM2 50-member smooth biomass burning forced response. They look different. They have different forcings. Then we have this beautiful comparison that Marika Holland and Jen Kay led, where they use CSM2, that is CMIP5 forcing. It's a 15-member ensemble, not quite as much, but I think we can be confident that this is a good estimate of the force response. So we really then have to now even think about when we compare models, it's really not just models, it's also the forcing. So this is the same model, different forcings, very different patterns, force response. And this is different model, the same forcing. So I just want to highlight it because I think it's very important. I will skip CVDP for large ensembles, but a lot of the plots I've shown you can be automatically generated with this package. And it's just a really nice tool. Okay, and tools and resources. I'm sure everyone knows this. And then force MIP. Rob's has a poster on force MIP, so I think maybe I shouldn't take much time, but I just want to give you a flavor for where state-of-the-art methods are at. How well do we do? So these are linear trends from 1950 to 2022. And this is one member of one smile. None of the participants knew what that was. Only Adam and Phillips and I picked the member. So we're the only ones that know what model and what model smile this came from. So these were the trends in that sample member. And so each participant was asked to determine the force component of this in the sample member with no knowledge of the truth, the true test of the method. The methods were developed on a set of training ensembles and evaluated using a different set of ensembles. No knowledge of model identification and gridding was all removed. This is the force response. This is the ensemble mean from the model that sample member came from. That was unknown to participants. And that's the internal component. And we picked these members because the internal component is big and it can resemble the force response. That to me is one of the most insidious things. If the internal variability of trends that we happen to have resembles the force response, I think we're really challenging our methods, and that's something we have to confront in this model workshop. So I won't go through any details, but these are 9 methods that were developed after the hackathon. So they were just submitted a couple of weeks ago, and you don't need to know who did what and what the methods are. You just need to see that there is a variety of response, and one of them that is quite skillful, but the others really, there's a wide range. And then for temperature as well, there is a wide range. So I'm going to leave it at that, and you hope to speak more about see Rob's poster on Friday. And this is the estimated force response for that canonical picture now of the trends based on 9 methods. So that's okay. I'm going to end, and I'm going to end with a sobering statement that was told to me when I was a graduate student. Eugene Rasmussen of Rasmussen and Carpenter was on my committee. And I remember one day he told me the lifetime of trend is the time it takes to be recognized. And I think that's also an important point to make for this workshop. Thank you very much.
Okay, so we're gonna go to the discussion phase. Clara, would you mind taking a seat in the front? Gavin, if we can get him up on the screen. I guess we should do that. Let's skip those. Oh, good. Yeah. Questions? So are there any questions in the audience for 2 plenary talks? Let's get it started.
I think online, Alyssa's paying attention, so please feel free to post your things in the chat.
Just as a reminder, we're going to use the ceiling microphones. Karen.
Yeah, I'm looking for Gavin, and I might be misinterpreting your sign convention, which maybe will be an easier answer. But in your series plot, you have shortwave versus long wave trends, top of atmosphere, observations from series and models. The observations show positive shortwave, negative long wave. And if I'm interpreting the science correctly, that actually says climate change is a shortwave heating rather than long wave heating, which is what we mostly could think about. And then the models are split across the signs. So some of them have, I think, on both shortwave and long wave, if I remember correctly. Just the sign seems pretty fundamental, let alone anything else. I just wonder if you can comment on that a little bit more.
No, I mean, yeah, I mean, you're correct. I mean, if you look at the components of the imbalance over the series period, the increase that we've seen in that imbalance has been driven almost entirely in the shortwave, and we think that that's going to be a combination of aerosol forcing, surface albedo changes, and also cloud feedbacks. And we haven't really got a good and robust breakdown of that as yet. But as you can see, in different models, given different SST patterns or with different forcings, the models can be all over the shop. Now, we are unclear whether we're doing the right comparison. We are unclear that what the structural uncertainty is in the series data. And so it's very hard to conclude very much about that until we've improved all of those different things.
Clara, you mentioned forcing uncertainty at the very end. So my impression was a bit that this usually does not get enough attention, and usually we only address it as like in sensitivity tests. So do you think, what is the way forward? Can we do this more systematically? And
Yeah, I think it's so important, and we wouldn't even have noticed it, right? If you don't go back and use the same model with two different forcings. I think maybe the low-hanging fruit are aerosol. I think that's probably behind at least some of that sensitivity to the different forcings. So perhaps at least our next step with CSM, or my next step is to just do a single forcing aerosol, withheld aerosol, using CMIP5 forcing versus CMIP6. I don't know. I think we should open it up for discussion. It's so hard to test these things systematically across models because it's just too much computational resource. It seems there should be more efficient ways to do it. I don't have a really good idea, but how do we do this in this efficient manner?
Yeah, I'll just follow up on that. The uncertainty in the aerosol forcings are much larger than just the biomass burning, and we are not sampling them. And so we have these great new large ensembles, but they're initial condition ensembles. They're not forcing ensembles. And I think that there is a significant component of many aspects of the climate that are going to be affected by a proper forcing uncertainty ensemble that we are not currently doing.
There's an online question also related to the forcings. Sonia, are you able to unmute and ask it? Shall we ask it for you?
Do you hear me now? Yeah. Yeah, okay. Yeah, so as also a question on the forcing. First, yeah, I really enjoyed both presentations from Gavin and Clara. And so I had a question actually to Clara on the forcing effect, because you showed mostly the effects over the oceans, SST in CMIP versus CMIP6. Of course, I'm wondering, did you find also strong differences over land?
Thank you for the question. Yeah, that paper was just focused on the SST. I believe so, but maybe Isla remembers. I
think it kind of warming over Eurasia expands into the ocean, so that difference gets solved with the oceans. I think they're in the land too.
Yeah, these are available to anyone. This multimodal large ensemble archive that we have. So please, and there's a similar one for CAN-ESM5, I believe. Also did this swapping of CMIP5 and CMIP6 forcing. I did want to comment on initial condition. I think, Gavin, you mentioned it. We do have to pay attention when these large ensembles are initialized. They're initialized in 1950. There may be memory for at least a couple of decades in some regions. I'm not worried with CSM1, which were initialized, 1920, and CSM2 in 1850. but it is something to pay attention to.
So I have a question for Kevin. So you were saying that the models are wrong and observations are also noisy. So it seems that at least in terms of models, we are a little bit confident that we can do the modeling like sensitivity experiments to figure out this kind of uncertainty is coming because of the internal variability or the forced variability. But how about the observations? How to overcome the noise that is coming in the observations? Is it because observations is only one simulation, or you could say only the one type of we have the observations. So how can we know that this is coming from the internal variability, or it is due to the forced variability, or the trend is coming because of what reason? So how can we take in the observations to remove the noise at least in the trends or something?
Great question. So often it's very hard to do a proper systematic uncertainty approach for an observational data set. We're doing something pretty exciting with the GIST-TEMP data set, where we're building a Bayesian Monte Carlo, all the different decisions that go into making a reconstruction, so that you'll get a set of ensembles for the observations. But most observations are not going to be able to do that. And so as a poor man's substitute for having a good estimate of the structural uncertainty, we can take different observational products. So for a long time, we looked at different estimates of the surface temperature trend. We can look at different estimates of the clouds properties trends. We can look at different estimates of the water vapor trends. And while that does not determine what the true structural uncertainty is, it gives you a sense of at least the minimum amount of leeway you need to give the models before you go too much. One of the things that happens if you only have one observational data set is that we tend to overfit to that one observational data set. And that can really bias things. And so in our assessments of model skill, tuning, all of those kinds of things, we are very much trying to use multiple data sets where they are, and where there aren't, we're trying to make reasonable assessments of what the true structural uncertainty is. And that's an ongoing issue, and it's something that we need to be discussing with the observational community more and more, that we don't just want their best number, we want to know really what the uncertainty is around those numbers.
I think, Tinka, you had your hand up.
I have a question for Clara. On the precipitation impacts over the European region, you showed, so the first row was the two extremes of the distributions of the models. And I was wondering, since those two patterns, they were associated with different SLP trends, I was wondering in those two realizations, what was the state of the AMOC trend? Was it really, or SST mediated by the AMOC?
I don't know.
Okay.
Good question.
Yeah, because that seems important for impacts on precipitation. And also had another question related to that. Then the row below was it seems like I have to admit, I'm not familiar with the method, but it reminded me of the moisture budget that Richard Seeger used in many of his papers, in which he divided into thermodynamic and dynamic components and transit eddies. And I was wondering, is that more specific to estimate the forced response, or would be comparable in principle with that method?
Yeah, I think it's very different. I think the moisture budget is very insightful. Obviously, then you can, parse, is it anomalous atmospheric circulation trend, or is it this change in moisture content with the same atmosphere, no trend in atmospheric circulation. So that would be a nice diagnostic. But this observation large ensemble is not at all along those lines. Think of the observation large ensemble as a plausible way to reshuffle the phases and of internal variability, which the unforced internal variability can, right, just have different sequences since it's unforced. And so that's the premise of the observational large ensemble. We haven't done a moisture budget at all.
I meant the thermodynamic.
Yeah, I'm just calling it thermodynamic because there is no influence from atmospheric circulation. So it's the residual from that. I'm calling it thermodynamic.
Okay.
But I haven't done a moisture budget. Thank you. Yeah.
Thank you for that really wonderful talk. You mentioned the challenge around looking at natural modes of variability in a context where the climate system is now sort of in a no analog state. There is information presumably one could use to look at that problem by looking at a pre-industrial control, which is, and then comparing that with say an instantaneous 4x CO2 run. So you look at what the modes of variability would be like in a new, much warmer climate. And then third, a 1% CO2 run where you're really hammering the system with very large trends. Have you tried, the advantage of that in that context is that the signal should be very large and blindingly obvious. And the forcing is pretty well known. Have you tried looking at what happens to natural modes of variability in that context?
Yeah, so I didn't mention it, but I think that is a fantastic usage of large ensembles. We don't have to just rely on, pre-industrial or 2 times CO2 or compounding CO2. So if you have a lot of members of a large ensemble, you can do what we've done some work using snapshot EOFs. So at each point in time, you can string all your ensemble members together. Say you have 50 of them. Each of them at a given point in time will have the same common force response and a different phase and amplitude of internal variability. So do your EOF that way. That's get the leading modes of variability, say in 1920. Do it in 1921 and just march through the entire historical and future climate record. That is just a beautiful way to assess the evolving characteristics of internal variability and how forcing affects those characteristics. And I think that is something, just a really nice, next, digging into these large ensembles, not just to look at, static view of internal variability and force response, but how they co-evolve together. And in that case, models are all over the place in showing different force responses of ENSO. And that then rears its ugly head for the global modes of variability because ENSO changes differently in each model.
Okay, this is, I guess, a comment. We've heard it's an obvious comment, but also at the beginning of the meeting anyway. We heard about structural uncertainty across the CMIP, uncoordinated structural uncertainty. We've heard about initial condition uncertainty, this observational uncertainty, both of them we don't actually understand, but we don't exactly what observations are. And then there's what Clara mentioned, the fact that there's different ways that could have evolved. I'll just raise the other one, which is obvious, which is parametric uncertainty, which is potentially just as big as all these other things that we haven't really addressed it very much. Gavin could have mentioned it, Gis has done some work on it, but I think it's completely, and there's also forcing uncertainty, so I forgot all the uncertainty. So just to depress us even more about the complexity of the problem.
Okay, one more last question. Yep.
I have a question regarding the forcing. So it's my question?
Yeah, go for it.
Yeah. So I have a question for Clara. So for the forcing, the significant effect from forcing. So to my knowledge, we barely have any accurate observations of exoplanet aerosol emissions in the historical period before the recent decades. So as you have already shown that the forcing is really important and the aerosol is kind of the most important forcing factors. So how can we improve our model or build a kind of an accurate model based on a totally unknown of the forcing, one of the most important forcing factors?
It asks the same question. And especially with, maybe sulfate aerosols, we have a bit more constraint. It's really outside of my realm for sure. And then black carbon, biomass burning. I mean, there's just, I don't know where the numbers come from. Right, should we even not use them? I mean, we really have to talk about this.
So I have some good news, right? So we just launched a satellite a month ago, the PACE satellite, which will, when it starts to produce data, which will be in a couple of months, and I hear it's going quite well, will produce global three-dimensional maps of aerosol composition. Not just total aerosol amount. And that will be, I think, give us the possibility to really narrow the uncertainties in the baseline composition that the models have, which varies enormously. Part of the reason why some models are much more sensitive to aerosols than others is because they have a very different total amount of aerosol, the way that it's spread between sea salt and dust and sulfate and nitrate and black carbon and all the rest of it. So these things will there is new information that will come to be applied, and that will allow the models, I think, to narrow, not entirely, because the aerosol cloud interactions are still going to be very difficult, but we'll be starting off with an estimate of what's in the atmosphere that's much closer to the real world, hopefully.
Great. On that positive note, we're going to wrap up the discussion. And we're going to transition to the new section on trends in the meat state. So let's thank both speakers.
Thank you very much.
So I'm Angie Pendergrass. And I'm Kevin Grice, and we're co-chairs of this session on trends in the meat state.
Our first speaker is Maria Rugenstein.
Yeah, so each speaker will have 15 minutes. There's going to be 3 talks before the break, then we'll have a half-hour break, and then 2 talks after the break, and then time for discussion. So particularly for the talks before the break, make sure you write down questions so you remember for the discussion after.
Thanks for having me. What a great crowd. I think we could stop the program right now and just chat. Excited to be here. I thought I have a break and was totally chilling out in the back. And 20 minutes, right? So I will be talking. So this is all work I'm showing is in collaboration with Joe Olancheng and Clara Deser, who both have posters today online on exactly these subjects, and Mark Alassi, who is a grad student at CSU. And I will be talking about top of the atmosphere radiation trends, surface temperature patterns and how the two are connected, and then if I have enough time, how the discrepancies between observations and models in these quantities may relate to projection uncertainties. So Tiffany said I should say something good, so I thought I started with that. Global mean surface temperature, which is what the models were developed for. Maybe it's not too impressive that they're doing good. So black is the observations, and this is a trend over the last 20-ish years, 23 years. And the colors are large initial condition ensembles. Each dot is one ensemble member throughout the talk. And in general, throughout the talk, my requirement for good or bad is actually very, very low, is do the observations fall within the range of the models, period. I don't care about whether the trend is false or not. I just want the observations to lay within the model space. And for the global mean temperature, I think they're doing okay and fall around both sides of the observations. Here's the bad. This is top of the atmosphere radiation. And I didn't see Gavin's figure, which should have looked similar, I guess. So it's actually really a problem. First, the trends in the models are less than half of what they should be. The series it's in an extremely conservative uncertainty range. So probably actually all of the model ensembles are not even close to the observations. And the problem is that the models agree in the bias. This I find very concerning. So we have a bunch of issues where we know the models are bad in like precipitation or aerosol forcing, but usually they fall around the observations. And here they agree in the same very strong bias. So what we do in this paper is developing a new bias method of trying to put in some physics of the connectedness between surface temperature trends and top of the atmosphere radiative trends on a local level. So what I will show in a second is if an ensemble of a large initial condition ensemble gets the surface temperature right in one location, how far off is the top of the atmosphere radiation in that location, all in trend space. So 0, 0 is good, and we want the ensembles to lay around 0, 0. And this is just for one location, which has the strongest trends in the observations and be specific. So this is what the models are doing. And again, we want the observations only with laying comfortably in the range of the models. So if they get the surface temperature correct in that region, the top of the atmosphere radiation trend is the 1 or 2 or 3 watts per square meter off. And this is doing this measure across all the models, but this is very robust if you do it for each single model. Now we aggregate that measure globally and go to Dirk's poster to learn about the details. So this is what I show on the horizontal axis here is this response bias measure we introduced. And this is plotted against the radiative feedbacks of each model and ensemble member. So now comes the ugly, that radiative feedbacks are extremely noisy, which isn't surprising because we're regressing 23 points against each other, right? So radiative feedbacks are dRdt, dr being the radiation imbalance I showed before, the n accounting for the forcing, which we have for most of these models. And then regressing this against the surface temperature change. So if you took the observed radiative feedback, the dashed line here, which is equivalent to just one single ensemble member, you would say the models are all or mostly too stable. So a negative radiative feedback means a rather stabilizing atmosphere. So this would imply a lower climate sensitivity. However, if you use something more accumulated or integrated or a bias measure, you would say that the models with which have a smaller bias of the connectedness between the surface and the top of the atmosphere tend to have more stabilizing feedbacks. And now it's actually nice, this is the only time we talk about the forced component, that we have these large ensembles. So the mean of the ensemble members should be very close to the force response and to the inverse of climate sensitivity, disregarding forcing uncertainty. So you could basically flip here climate sensitivity on the vertical axis. So we say, or we need to show that the models which have a lower climate sensitivity tend to be able to reproduce the sensitivity of the radiation to surface temperature trends better than the models with higher climate sensitivity. This could be that these models have better cloud physics, or it could be that they have better climate sea surface temperature pattern, because that measure is a local measure, but we know that radiation depends not only locally on the conditions at the surface underneath, but also on remote locations. So this is the second point I would like to go into, is how wrong are the models actually in reproducing observed SST pattern. So for radiation, we are bound to these 20-ish years just because we only have the series observations. But for surface temperature, we can go farther in time, which is what I will be doing now. So probably this plot will be shown 20 times in the next couple of days. This is the last 40 years observed sea surface temperature trends. And there has been a lot of debate about this, whether or not the large ensembles do capture which parts of these patterns. So what we did is generalizing and not picking always these 40 years, but looking more systematically at all possible trends, starting from 1950 through today. So I will depict this as a
tons of trends, different starting and end years. And this is observations only. And just for time, I will show only the East minus West Pacific, the two boxes, because these regions are very relevant for the pattern effect, for the sensitivity of mostly the clouds and the lapse rate to the surface temperature patterns. This is how the observations look like. So there's a lot of information in here. Blue means a strong a negative gradient. East minus west is negative, and these on long time scales are slightly, not actually very strongly negative. And then on the diagonal here, you could almost put PDO on top of it. So we had a strengthening of the gradients. If you take any trends around the year, around the 60s, and then you had a weakening of the gradients around the 80s for a long time, and then you had a strengthening again around the year 2000. This is what most people are talking about. And actually now, for 20 years, of the last 20 years, you have positive gradient again. So how do the models do in this? I again depict this as dependency of start and end year. And now the measure changes. So we have 15 large initial condition ensembles. And for each ensemble, we fit a normal distribution. We take 3 SST data sets and average them and say, do the observations fall within or outside ±2 standard deviations for that specific model's distribution? You can be stricter on this or not. It doesn't really matter. The normal distribution is not a great fit for some 2 standard deviations are not even within the range of the model. Yeah, so it doesn't really matter. This is how they look like. So purple means bad. Purple means 15 models do not include the observations within ±2 standard deviations. So the long-term trends are really bad. None or very, very few of the models can reproduce them. And as expected or discussed for these more decadal length trends, almost all the models do not get the strengthening of the gradient around the year 2000 and around the 60s. But then this is a little subtle here, about half of the models do also not get the strength, the strengthening of the gradient around the 80s. And the different letters here, different papers claim that the large initial condition ensembles can or cannot capture the trend, so it really depends on the way you're looking. Most recently, they are really, really good. White is good. All the models get the strengthening of the gradient. But whether or not for the right reasons, we don't know. So whether this is the starting of the forced response looking more El Nino-like from being more La Nina-like, or whether this is just another PDO phase, I think is almost impossible to tell, but maybe Alexey will tell us. I went into this with the hypothesis that the hot models, because most of these are CMIP6 models, that the hot models want to be too quickly into a El Nino-like warming state, and hence they have a harder time doing the strengthening of the gradient, so they cannot reproduce this. This turns out to be true, so I'm testing I'm sampling kind of these 2 strengthening and weakening of the gradients here now. And when the gradient strengthens around the year 2000, it is true that models with a higher climate sensitivity tend to have the observations farther outside of their distribution. So this is sigma here. And I would say 1 or 2 is all good. It's not that 0 is the best, right? We know it's not all forced, but it would be nice if they're within 2. But they are here. Indeed, alpha lunch. However, the same is true for the period more around the 80s, where we had a weakening of the gradient. And the hot models also cannot reproduce the weakening of the gradient, which they should easily do, right? Because they are in a more El Nino state anyways already. But it seems like that the hot models have an issue with reproducing the swings of the gradient. And our current hypothesis is that this is due to the relative relevance of the the SST feedback versus the lower tropospheric inversion strength feedback from shallow clouds. How much time do I have? Is it 7 minutes? Yeah, 7 minutes. Then I will tell you something about the future. I wanted to leave enough time for the summary. So my third point would be, given the radiation is very off, the SST patterns are off in very relevant regions. If these two problems persist, what do we do with projections, right? And this is all on a global level, like this really matters. Like, people should get this right? This is what they were built for. It's not the Amazon tree right here dying. Do they get it right or wrong, right? And you can translate this global number to your local problem, whether or not it might matter for some problems or not. Anyways, I think this is important. So the question is, if the models are as bad in the SST pattern distribution in the future and in the radiation, how do we interpret projections or add that additional uncertainty we learned about over the last couple of years into projections? So what I showed is that they are bad in radiative feedbacks. What people are talking about, this is really the pattern effect since a decade or so, is that models, that radiative feedbacks do depend on SST patterns. So if you use AMIP simulations, these are AMIP, every single gray color is one model. And if you prescribe observed SSTs over the last century, they wiggle around in pretty much a very similar fashion, very uncertain still. But the models agree that they tend to be more and more stable with time. We don't have observations to say whether this is right or wrong. And then for the future, we also know that the models agree in that if you hit them with a step forcing of CO2 through time, idealized time, potential relatable to the future, is that they get less and less stable. So more and more positive. So the question is, what will they do right now in the next 20 or 40 years? Given that they are already in, that the coupled models not forced with the right SST pattern are already in a wrong state. So what we are, I won't explain this in depth, but we are using Green's functions, meaning we take a climate model, fix the SST, force it with a patch of SST warming somewhere, let it run to equilibrium, do this everywhere, fancy and nice, and get this matrix of the dependency of, in our case, radiation, or really any climate variable on the SST forcing anywhere else. So it's a really beautiful matrix, probably wrong. The setup is so idealized, but it's kind of like a climate model in one matrix. So you see here, if you warm the West Pacific, let's say, 1 degree, the global integrated, the global sum of all radiative feedbacks will be stabilizing, blue. But if you would only warm the East Pacific, the global integrated radiative feedbacks would be positive. So if we only warmed here, we would be in a runaway hot world already. So what we do is taking a climate model, taking our matrix and involve it with observed SST pattern. This gives you the radiative feedbacks, which get more stabilizing in time, same as up here. If we plug in or convolve that sensitivities with the SST pattern the model wants to be in, that's the ensemble mean of MPI-ESN, doesn't matter. It wants to become more, less stabilizing with time because it's the forced response, and this is true then for the future as well. So the gray line future with the uncertainty of the large ensemble in gray. And now we are trusting the model in that we said the global mean temperature will be all right. We just reshuffle where the model warms. And we do this tiny little bit, 3%. We take out a little bit of warming out of the West Pacific and put it into everywhere else, or into the East, or do this 100 fancy physically reasonable times. And the green range is what you get when you take out or put in extra heat into the West Pacific or take it out of the West Pacific. So you get a huge range in the radiative feedback change just from this. Orange would be the East Pacific, blue would be the North Atlantic. So now we transform this into temperature space, and what we get is that the gray line, the gray arrow, is the uncertainty towards the end of the century of global mean temperature in RCP 8.5 of internal variability. This is just what the model wants to do. And if we reshuffle 3% of the warming, we already increase that uncertainty a degree. This is extremely conservative. So this just tells you the degree to which the SST patterns matter. But now we are stuck with this problem that currently, like today, this is the center of a 30-year regression because we're talking feedbacks. But this is where where the observations are. This is where the model is. So to overcome that, we already start from the wrong situation. We take our observed SST pattern and we interpolate it from where we currently are to where the model wants to be in 30 years and 50 years and 100 years. So we trust the model in the future, maybe, and say, how do we get there from where we are currently? A more negative assumption would be we stay, or actually it's positive, we stay in this observed temperature pattern and we just assume we would keep that pattern constant. Assume it's the forcing, this would be great. And this would result in this constant feedback parameter here. So again, if you're not used to looking at feedbacks, temperature might be easier. Global mean temperature. The dashed line here is the temperature we would have if our observed SST pattern would be staying stable as it is. Same RCP 8.5 forcing. So just through changing the we could reduce the warming a degree. This is why it would be good if it stayed like it is, because it actually, through cooling in the East Pacific, where we have positive feedbacks, we kept the global mean relatively cool to what it could have been if there would have been warming in the East Pacific. Okay, and then for the for transitions, these different lines, the details don't matter so much, but if the SST pattern in the models, no, in reality will look different from the models and warm faster, for example, in the East Pacific, our warming, global mean warming rates will be extremely substantially different from what the models project currently. So there's a bit of a timescale issue here because we have observations for tier irradiation for just the last 20-ish years. For that time, all the models seriously and underestimate the heat uptake of the entire climate system. Feedbacks, however, calculated through that short times are kind of meaningless or too noisy. For surface temperature trend in very relevant regions, the models also agree in not being able to capture them, but it is very time period dependent. For that, for the more decadal time scales, we do not know the feedbacks though, so there's no way to really verify them. So it's a little bit of it's a big conundrum. And that very likely matters for projections, which I think are way more uncertain than we think if we just trust the models. And there seems to be a tendency that the observations do have a very strong heat uptake of the entire climate system, most likely dominated by the ocean, balanced by a strong radiative feedback. And the models don't get that right? They get the global surface temperature right. They shouldn't, because they're so often the radiation. So this means they compensate somewhere else, most obviously in the ocean heat uptake, balancing their wrong radiative feedbacks, leading to wrong SST patterns, maybe. That's it.
I think we're gonna hold questions until the discussion.
Yeah, yeah, and we forgot to mention that Maria had an invited talk. So the next talk is by Stephen Po-Chedley. Title: Persistent Differences in Simulated and Observed Tropical Tropospheric Warming. So yeah, thanks very much, Stephen. And it's 15 minutes, so 10:22. Yeah.
So just first, thanks to the organizers for arranging this amazing workshop, and also thank you to my collaborators listed below for their help in putting together this research. Today I'm going to talk about MSU observations. So these are microwave observations, microwave sounding unit, that measure the deep layer tropospheric temperature from the surface to the tropopause. And I'm going to be talking about a problem that has existed for a long time with these records, in that they show less warming than models and have done so for a long time. So in CMIP3, the multimodal average trend was 2 to 6 times greater than the observations, depending on which data set you looked at. In CMIP5, this number went to 2 to 3 times greater than the observations. And this issue has been popularized over the last couple decades from plots like this from John Christie. Here he's plotting the model simulated tropical tropospheric time series, and the dotted lines, the observations are in solid. Okay, and so the models with the dashed lines and the multi-model mean is in red, show much more warming than the satellite observations, weather balloons, and reanalyses, with the solid lines at the bottom. And only a couple CMIP5 models reproduce the observed trends. And this issue has even been shown in Congress, and this is brought up every year. This issue has persisted into CMIP6, so this is a figure adapted from McKittrick and Christie 2020. They're showing that the global rate of tropospheric warming on the x-axis scales with equilibrium climate sensitivity across 38 CMIP6 models. And when they plot the mean of the satellite observations, they state that all the models were more than the observations. And so this suggests to them that climate sensitivity is too high in CMIP6. We looked at this with a much wider swath of models. So this is a distribution of tropical tropospheric temperature trends from about 500 CMIP6 simulations. And when we plot the range of observations, we see that there is overlap between the models and the observations. So about 10% of model simulations fall within the observed observations. The models still exhibit about twice as much warming as the satellite observations. So this isn't necessarily a statistically significant difference, but we still wanted to understand why there's this offset. So we started to look to see if internal variability played a role, and we used the CSM1 large ensemble to investigate this. Here I've just flipped the axis, so the distribution of CSM1 trends are on the y-axis for tropical tropospheric warming. The satellite observations are in purple. And there's a really large range of trends across the CSM1 large ensemble, from about 0.2 Kelvin per decade to over 0.3 Kelvin per decade. And this warming scales with warming in the Central Pacific region. And if you look at some of the end members, the members that show less warming due to internal variability, they generally have a pattern that looks like this La Nina-like pattern, where there's a lack of warming or even cooling in the Central and Eastern Pacific. And the bottom plot shows the equatorial ocean trends to 300 meters, 5 south to 5 north. And this really stands out compared to the ensemble mean, which is a homogeneous warming pattern. And if you look at the observations, they look a lot like member 8, so this member that had reduced tropical tropospheric warming due to internal variability. So we see that in both the observations and member 8, there's a lack of warming in the Central and Eastern Pacific, enhanced warming in the Western Equatorial Pacific at a depth of 150 meters, and enhanced cooling in the Eastern Equatorial Pacific. And so it looks like internal variability has likely reduced the observed rate of warming in the tropical troposphere based on this pattern matching. But the question is, how much did internal variability reduce satellite air warming of the tropical troposphere? So to try to get at this question, we used a statistical learning technique. And the goal was to take the pattern of warming, so that's our predictor matrix, and predict just two things based on one map. What was the force component of the tropical tropospheric temperature trend, and what was the internal variability component of the trend? And this is motivated by the previous slide where it looks like patterns can tell you information about the relative partitioning of the warming of those two components. So we use PLS regression to make this connection between the pattern and the two components of the warming. And to do that, we trained across a lot of model data. So we sampled different 36-year time periods, 36 years because we were looking at 1979 to 2014, it's 36 years. So we sampled lots of periods within the historical experiment to build up a training data set. We sampled across 14 different climate models and 10 members per model. So we had about 3,000 samples with which to try to make this connection between the pattern of warming and the components of the tropical tropospheric temperature trend. We used a leave one out approach. We had 14 climate models in all. So we trained on 13 of the 14 and then tested to see how well we could identify the internal variability component in the model that was left out. And we did this iteratively so we could see how robust our results were across models. And so the eventual goal is to try to say something about the real world. So if this works in models, we're going to take our model trained PLS regression and apply it to the observed record to see what that says about internal variability in the observations. So this is an example output from this PLS regression model. It's for Access ESM 1-5. And so we've trained on all the model data except for Access, and we've tasked it with taking in maps of the pattern of warming. We've passed in 40 maps of the surface temperature trend into our PLS regression model and predicted the internal variability component of tropical tropospheric warming. And so that's the value on the x-axis is the prediction for internal variability. And then because we're using a large ensemble, we can tell what the actual internal variability component of the trend is. So that's the value on the y-axis. So in this case, we're well correlated with what it should be, but we're a little bit off the one-to-one line. So our prediction is a little bit too far in the lower right quadrant. But we did this iteratively, so it works a lot better with CSM2, strong correlation, mostly along the one-to-one line. We just went through and tested this on all the models. In general, the correlations were pretty high, mostly along the one-to-one line, but there is overall a slight bias when you fit all the model data. But this worked well enough that we wanted to try to apply this model-trained PLS regression model to the observations to see what it said. So then we take maps of the observed change in surface temperature. So this is from HADCRUD 5. We pass it into our PLS regression algorithm and get an estimate for the predicted internal variability component of the trend. So that's the distribution along the x-axis. And we get a distribution because HADCRUD 5 has 200 ensemble members. So we actually passed 200 maps of the warming trend into our statistical learning model and got a distribution of trends. But we know from testing on models that there were errors in the prediction, which you can see from the scatter plot. And so the next thing we did was we convolve the predictions along the x-axis with the error in the regression to get a bias corrected estimate for the internal variability component. And that's the PDF on the y-axis. And we did this for different surface temperature data sets so we could see the structural uncertainty. And overall, we get an estimate of negative 0.07. So internal variability has reduced the real world tropical tropospheric temperature trend. So we can go back and look at how this affects the model observational comparison. This is the figure I showed before of tropical tropospheric temperature trends. And now we're just going to subtract off our estimate for internal variability with the uncertainty. When you do that, the observations and the models agree much better than uncertainty. And then the other thing to note is that, as Gavin showed, there's a lot of Wolfpack models with high ECS values. And those are outside what we expect for ECS. So if you look at the force trends from models with ECS values around 3, they tend to fall well within the observational range. So if you account for internal variability, this makes the model observational comparison much closer. Just want to quickly touch on 2 other issues. That's the role of forcing biases. So John Fasullo in 2022 looked at the rate of warming in CSM2 versus CSM1 in the best observations in back. So this is for the Northern Hemisphere extratropics. And he showed that CSM2 warms much more quickly than the observations starting in the mid-1990s. And so he was able to work with collaborators to pinpoint this to the biomass burning aerosol emissions. There's a spurious increase in variability starting in the mid-1990s, in 1997. And you see that from the Maroon curve on the right-hand plot. And so what he did was he smoothed the biomass burning aerosol emissions to get rid of this discontinuity and re-ran the CSM2 large ensemble with collaborators. And he gets this CSM2 SBB curve. So that's the smooth biomass burning trend or time series in the Northern Hemisphere extratropics. And so he shared this data with us, and we looked at how this affected tropospheric temperature trends over 1979 to 2014. And we get this map here. So this is the estimated bias in the warming rate in the troposphere due to this discontinuity in the biomass burning aerosol emissions. So it tends to inflate trends in the troposphere. And even though it's largest in the Northern Hemisphere, it has a big effect on the tropics too. So it inflates tropical tropospheric temperature trends by about 0.04 Kelvin per decade. And so this was only in CSM2, but he presented evidence that this affects other CMIP6 models as well. So we know this is an issue for CSM2, and it may affect other models and be a systematic bias. Okay, the last point is that there's also a role for observational biases. This figure is trying to do something similar to what I did before, except I'm just trying to estimate the total tropical tropospheric warming based on the surface observations. So this is in models, and you can see that you can very accurately predict tropospheric warming if you know the surface temperature trend. And I mean, we know that the troposphere is tightly coupled with the surface. If you just multiply the mean surface warming by 1.6, you'd probably get the same figure. But we use maps of surface temperature change. So the next step was to pass in the observations and give an estimate for the expected tropospheric warming given the surface temperature trends. And when we did that, we got a value of 0.19 Kelvin per decade. So that is the expected tropospheric warming based on the surface temperature change. But we also measure the tropospheric temperature change. So that's this purple shading here. So this is from the MSU microwave sounding unit observations. And these observations come from 4 different groups. So NOAA is at the top, and that's in line with our expectations for the tropospheric warming in the tropics from the surface temperature observations. UW and RSS are at the edge of our expectation, and the UAH trend seems too low given the surface temperature observations. And then this is also backed up using water vapor measurements. So if you look at, in models, the simulated water vapor trend compared to the tropospheric warming trend, they're also tightly coupled together. And so what we did was we looked at we had one water vapor data set from RSS, and we looked at the trends in the troposphere too. So one water vapor trend shows 1.5% per decade change in poisoning, and the troposphere temperature trends vary from 0.1 to 0.25 Kelvin per decade over this time period. And the NOAA trends seem to be most in line with our expectations for models. So again, it looks like the upper end of tropospheric warming is in line with our expectations. There has been a change over the last year. The NOAA data set went from version 4.1 to 5.0. And the trend has dropped dramatically. So the NOAA data set has moved away from our expectations and shows much less warming. So this is, to Gavin's point, that there's really large structural uncertainty in these records. So with that, I will just briefly conclude. Our results indicate that internal variability has offset the force component of warming by about 25%. So when you account for that, the observations move closer to the models. And this is especially true when you account for the ECS bias, or the fact that most models have, or some models have really large ECS values. And so if you look at the models within ECS values in year 3, the models and the observations agree pretty well. We don't know the effects of this biomass burning aerosol discontinuity across CMIP6, but if it affects other models, that would also push the models closer to the observations. And then last, satellite observations are very uncertain. It seems like they should have large trends, but they're very uncertain. And so this is an issue that we still need to contend with. All right, thank you.
That look good for the people online.
Okay.
Hello, everyone. It's my pleasure to be here. And I'm going to talk about the topic mentioned by all the speakers so far. So the trends in the Eastern Equatorial Pacific, the past 30, 40 years, and the strengthening of the water circulation in the atmosphere. And I will focus on the topic of ocean thermostat versus nature variability. And I will go back from models to observations. And the home take message of my talk really that to describe recent trends, you really need to have both. You need to have climate variability, a PDO, Pacific Decadal Oscillation like signal, and you need a forced response of the system of ocean thermostat like physics. And before I start, well, I should acknowledge Ulla Hidi. She was my PhD student. She graduated a few years ago. She did a great work on this. And also I want to acknowledge Natalie Burles, with whom we started this work many years ago. All right, so different colors, but the same story. General warming in the observations, but the eastern central equatorial Pacific is getting colder, and the region of the coast of South America is getting colder as well. Versus what CMIP6 models simulate for this period of time, historical simulations. A little bit of warming in the east, if anything, but nothing compared to observations. You go to the future, it's really an enhanced warming in the eastern equatorial Pacific, the weakening of the water circulation, and the pattern, if you remove the zonal mean, looks something like this. So we really have to resolve this issue. What it is about the observed trends, variability, model biases, anything for us to be confident about this future projections of the eastern equatorial warming patterns. Right, so these are these observed trends. Again, you can take different periods of time. You can start from 1990. You can take 2013. You can go to 2023 or 24. The general pattern is more or less the same. It's this pattern with cooling in the east and warming in the west and the Indian Ocean. You can take the indices, like Maria did, for example, Western and Eastern Equatorial Pacific, and compare the gradient, east-west temperature gradient, to what models produce, and that's on the right panel. The red line is the observed strengthening of the east-west temperature gradient, and it goes something like beyond 2 sigma with respect to multi-model mean, which is the blue line, which is basically flat changes in this east-west temperature gradient. And then something I want to emphasize is not just temperatures, it's the strengthening of the water circulation. And on the right panel, it's a metric for water circulation, zonal sea level pressure gradient anomalies. And for that, the strengthening of the water circulation happens to be quite outside of any range. It's not 2 sigma, it's not 3 sigma, it's really an impressive strengthening of the water circulation. To show how bad or good, well, this is, I show it multi-panel plot, SST gradient changes on the left, east-west sea level pressure gradient changes on the right. For sea level pressure gradient, no models can even get close to the observations. For SST, most of the models do not get it. A few models that you can claim it is within the range of their ensemble members. And we use 3 ensemble members, if not obviously it's a limited number. But you can clearly see that in the majority of models do not capture this strengthening of east-west SST gradient, and no models capture the strengthening of Walker circulation. You can look at other variables. We just look specific SST gradient and sea level pressure gradient on the right, but we also looked at anything from zonal precipitation gradient and observations, ocean currents, omega at 500 millibars, OLR, and all these different variables, they indicate the strengthening of the Walker circulation over this period of time. Some of them are independent, some are semi-independent, but it is really very robust signal across all these different. Now, let me go back and discuss a theory of what should we expect from the tropical Pacific in terms of its response to radiative forcing. And there are 2 paradigms. One paradigm is going back to the idea of Amy Clement, Richard Seeger, Mark Kane, and other people, that you should expect some kind of ocean thermostat when radiative forcing is applied to the tropical Pacific. And the idea is, well, the West can get warmer because the East is controlled by upwelling. And if the West is getting warmer, then there is a positive feedback. Trade winds would amplifying upwelling. And so as a result, the eastern part of the basin along the equator would get even either colder or would warm not as fast as the West. On the other hand, there is this weaker Walker circulation idea, or eastern equatorial Pacific warming pattern. And in that paradigm, East becomes warmer. And it actually goes back to the work of Manabe and Stauffer, GFDO coupled models like 30, even more years ago. Typical response to global warming was Eastern equatorial warming pattern. And there are various ideas how it should work from the energetics perspective to a differential evaporating cooling. So cooling works, evaporating cooling works better in the West. So East becomes warmer. And there are other ideas, but that's basically 2 paradigms. And the majority of models, coupled models, tends to produce this Eastern equatorial warming pattern. Do models produce the ocean thermostat? Actually, some of them do. And this is these are 2 models, CSM1, 2 versions of CSM1, one high resolution, one lower resolution. And this is 1% increase on CO2 per year. And for the first 50 years, both models actually produced a transient thermostat or T response with the strengthening of an east-west temperature gradient. And it's quite pronounced. So 50 years of ocean thermostat, it's quite an important signal. And then eventually there is a transition to Eastern equatorial warming pattern. For one model, it's stronger. For one model, for the other, it's weaker. But there is this transient behavior, potentially. First, the transient ocean thermostat, and then the Eastern equatorial Pacific warming pattern. So, and just to mention the differences between the models, these two particular models. One model has a sharper thermocline, one model has a coarser thermocline, and the model with a coarser thermocline has a less of ocean thermostat because the east and west do not have a strong contrast really to produce the thermostat. Going back to CMIP6, do they produce this ocean thermostat? Some of them do, and actually, if you force the models with a hard 4 times CO2 forcing, 7 out of 40 models we analyzed produced an ocean thermostat like forcing in the first couple of decades. So that's the top panel, and it's not unlike the observations. The problem is there's only 7 models out of 4. Majority of models, like 10 models, produce in eastern equatorial warming pattern, and taken all together, they produce a weak eastern equatorial Pacific warming pattern. Nonetheless, there is this ocean thermostat response, and we will remember this, and I will use these models for the next part of my discussion. One more thing to say again, the ocean thermostat in models, even the models that have it, is transient. And so this is just an example of different experiments. And for 4 times CO2, you can clearly see this strengthening east to west temperature gradient initial, and then everything goes to the warming of the east. For other scenarios, you have a period of relatively flat, couple of decades of relatively flat temperature gradient, and that's sort of ocean thermostat fighting this eastern equatorial warming pattern. All right, and then again, in the end, warming. All right, now let's go back to the observations. And the idea is, can we really identify this ocean thermostat in the observations? And for that, we need really to think how to separate forced variability versus nature variability. And there are many ways to do it. None of those ways is ideal. And we used actually a very simple approach. So we separated the signal, we observed SSC trends, into a uniform warming, just very simple. And then we calculated a historical PDO pattern from the observations, from the same observations. It's panel B. And then we feed it this historical pattern into the observations. So that coefficient A, basically a coefficient that reflects this feeding. And that gives you the magnitude of this component of the trend. And then the residual. So the residual is panel T. So this is presumably the forced warming pattern. You can argue what about PDO or PDV, is it how much it is forced, how much is internal, but it doesn't matter. Historically, that's the PDO. So we separated the PDO, and then we have this residual. Presumably, again, the residual is a forced. All these 3 components, we have roughly the same magnitude. So all of them are important. And to simulate this eastern equatorial Pacific warming, you really need both the PDO and this residual warming pattern. And now I'm going to discuss this residual warming pattern. And so this is a blow up of this residual warming pattern. So clearly it has this cooling in the east, central Pacific, eastern Pacific, and off the coast of South America. It also has a warming in the Indian Ocean, the warming in the west, and then enhanced warming of the northern hemisphere versus the southern hemisphere. So what is this pattern? Well, what I submit is this is this ocean thermostat working in the real system. And the models at large are not very good of reproducing this. However, if we take those ocean thermostat, those 7 models I discussed before, which has a better ocean thermostat, and this is this historical trends minus this mean warming, it's actually not too bad. There are some problems with that. Like the Indian Ocean warming is not strong enough, the Western Pacific warming is not enough. But overall, the pattern is not too bad. So you get this preferable warming of the coast of South America along the equator, and this suppressed warming or cooling, actually cooling in the Southern Ocean. And what's even more amazing, if you take this ocean thermostat models and compare their response to 4 times CO2, it's actually quite have a very strong resemblance to what we see in the observations. Obviously, 4 times CO2 is like you're heating the system with a hammer, really. But it seems like it captures this spatially and even in magnitude, the pattern of what you expect. And this is this ocean thermostat, the strengthening of the water circulation, the warming of the Western Pacific and the Indian Ocean, the cooling of the Southern Ocean, which, because some work suggests that this cooling actually also affects this water, this cooling, especially of the coast of South America. But historically, the signal is not as strong, and that suggests that the models underestimate this ocean thermostat. You really need the stronger forcing. One last part of it, potential role of aerosols. We analyzed 12 CMIP6 models. They have single forcing experiments, aerosols, greenhouse gases. And what it suggests that aerosols, at least in the historical trends, work to suppress a little bit of this eastern equatorial warming, but it's quite not enough to really cool the eastern equatorial Pacific according to our observations. So you really need this ocean thermostat. All right, so my summary. So climate models at large cannot reproduce the observed trends. And it's because, we believe, because the observed trends combine this ocean thermostat response and the negative PDO phase. You really need both to have the strength of the observed pattern. The ocean thermostat can be forced from the models if you heat them sufficiently strong, with sufficiently strong forcing. Historical ocean thermostat is too weak, even in those ocean thermostat models. And well, this anthropogenic aerosols are just a wrinkle on the story. So thank you.
At your break, you know, we have 6 more talks, and then we have some time for discussion. And so the 4th talk of the session, and the first talk after the break, is going to be from Yue Dong, and the title is "The SAM and Southern Ocean SST: Consistency and Discrepancy Between Models and Observations Across Species." So, sure. Online, everybody. Online, what quick?
Yeah. Thanks so much for all the great talks in the last section, focus on the tropics, because I'm going to drive the gear to the high latitude oceans in the southern hemisphere, especially the Southern Ocean. And then I'm going to look at the SSTs and the southern annular mode SAM and associated asymmetrical winds. And this work in collaboration with my postdoc mentor, Colombia, and collaborator Boulder and The reason I focus on the Southern Ocean because, like the tropical equatorial Eastern Pacific, we also observe this massive and pronounced cooling trends persist for a couple of decades since 1980s-ish, despite of a global warming over this recent decade. And same issue, our couple models seem to have issues or struggle to reproduce this observe the Southern Ocean long-term cooling trend. This is just another panel from Rob Wilson's paper, which highlights the Southern Ocean. That's the average over the Southern Ocean. You can see the majority of ensemble members don't simulate that cooling trend, but instead massive warming trend over a year. But what caused this observed Southern Ocean cooling, and why do models generally fail to simulate that? Well, there are many proposed mechanisms, like the Antarctica meltwater inputs, like Gavin proposed, and some internal variability in the Southern Ocean due to the ocean convection. But there's another pretty popular and prevalent idea which links to the southern annular mode, SAM, and its impact on the surface wind. Over recent decades, this reanalysis has already shown this positive trend in the SAM, featuring this high to low single pressure gradient, along with the strengthened surface westerlies around Antarctica. And I should mention that this positive trend in the SAM is pronounced in DJF, which is largely attributed to ozone depletion plus some small components from internal variability and greenhouse gas emission. And the reason people link southern sensitivity to the SAM or the wind is because from earlier studies using abrupt ozone forcing runs or SAM step function analysis have found the Southern Ocean SST cooling response following a positive anomaly in the SAM, although only lasts for a couple of years, identified as a fast response and gradually or eventually replaced by a warming response in the Southern Ocean. And some theoretical framework have identified that the leading mechanism has been associated with this strengthened wind, which strengthened surface westerlies, enhance the northward Ackermann heat transport, which results in this sort of cooling on the fast time scales. Although longer time scales, it's eventually the Ackermann upwelling that gives you cooling on the slow time scales. But all this modeling evidence and the theoretical framework suggest that, or led to a pretty popular hypothesis that whether this long-term cooling trend we observed in the Southern Ocean might just reflect this fast time scale SCT response to the positive SAM, or it is maybe the SAM that drives the long-term cooling trend. Well, then my first question is, assuming that is true, assuming the observed SCT cooling trend in the Southern Ocean is indeed largely or at least partially driven by the fast time scale SCT response to the SAM, a positive SAM, then, well, since this is a model observation comparison workshop, let's look at models. Let's look at how models simulate this SAM modulated SCT variability compared to observations. And by asking that, my hypothesis at that time was that, well, we know models have biased long-term trend. Maybe that's because models have biased representation of this sensitivity term or this SCT regression. Maybe their sensitivity terms are too weak or too short in time. That's why models don't have sufficiently long enough or strong enough SCT cooling associated with the SAM. And the reason I focus on this term, the regression term or sensitivity term, because the other term, the SAM trends, in models are generally okay. So there's a comprehensive study by Darren Wolf, who looked at the recent trend in the SAM and then in the SAM associated jet strengthening and the jet latitude shift in observations and in a range of climate model simulations. And they further break down the SAM or this trend into seasons, into different basins. And it was their conclusion that in general, models are okay reproducing this observed zonal mean SAM index. And I also, well, in my study, I used this 10 semi-large ensembles, 100 ensemble members, and calculate this SAM trend in DGF, where you have the significant trend over a longer period, starting from 1950 to 2000-ish, and I found this reanalysis year 5, or doesn't really matter which reanalysis product you use, like within, well, comfortably within the range of model simulations. So just a second to check that the SAM terms in models are relatively okay. So let's focus on the sensitivity term, the DST to DSAM term. So here I'm showing you the monthly SST anomaly regressions onto the DGF SAM index in observations. So this is the observation. So you can say following a positive SAM anomaly DGF, you do see some SST cooling response average over the Southern Ocean in the same season DGF, which is consistent with the literature. And we found that this modulation or this cooling response persists probably only for 2 seasons, and at the end of the year, almost goes to zero, meaning that there is a modulation. The SAM does give you a cell motion cooling response, but this response or the modulation probably acts only onto seasonal or maximum intraannual time scales, really fast time scale response. So how do models look like? So these are large ensembles, like a couple of 100 ensemble members, and calculate each ensemble members and find actually models pretty good. They capture this fast time scale SST cooling response to the SAM. And even I take out some ensemble members and made some composite. Those ensemble members simulate a massive warming trend over Earth index. So totally different with observations. They don't get observed cooling at all. They can still capture this, or even ensemble members, some ensemble members overestimate this SST cooling response to the SAM. And almost perfect in magnitude, almost perfect in the time scales, which, well, I don't know if this is surprising to you, but at least suggesting that my first hypothesis didn't work because models do simulate that observed SAM modulated SST variability. And by breaking down to cooling models or warming models, we can see correctly simulating this fast time scale seasonal to intraannual time scale SAM modulation of SST does not guarantee models' performance on its long-term multi-decadal SST trends. So what's going on here? Models have pretty good sensitivity term. Models have pretty good SAM trend. They just don't have a good SST trend. Well, here our assumption is that observed SST trend is largely driven by the SAM associated cool. So maybe we should go back to this assumption and really revisit observation and ask, how much does this SAM associated cooling explain the whole observed cooling trend? To what extent does this term contribute to the total multi-decadal SST cooling trend? So here I'm really focused on the observation, no models, no model biases. And since we've done some linear regressions, we have a linear regression term, we have the SAM trend, you can easily well play with linear algebra and give you the SST trend associated with SAM and ask how much does it explain the recent observed SST trend. Well, but the problem is we didn't end up using that because, well, first, the third point is, first, the SAM index is just a simple zonal mean set level pressure gradient. It doesn't really tell you much about the spatial patterns, which I care a lot about. And second, here I'm showing you the SAM index, normalized DGF SAM index from reanalysis. And DGF cell motion SST index, just average in SST in blue and the SAM index in black. And you can see these two terms both have mixed variabilities, both ranging from intraannual variability to this multi-decadal or low frequency variability, showing this 10-year running means. And here I mostly just cared about the low frequency variability because we want to understand the multi-decadal trend. And here, well, before I go further, the interesting thing is the low frequency variabilities in these two terms, you can see they don't really align with each other. So if you just simply take a period, say 1970 to 2000, where the SAM trend is most significant, and you multiply this regression, you probably end up with a strong SST cooling trend. But in reality, the cell motion cooling or cell motion temperature actually goes up and down. So probably not super perfect to just pick a period and then calculate the trend. So motivated by all these caveats, I decided to bring in this low frequency component analysis, which has been nicely described and applied in some of Rob Wilson's work. So I won't go into too much details into the methodology. Basically, here you can think of this approach as advanced UF, which gives you the most variability. But unlike the traditional UF, which rank all these modes based on the total variance explained, this method ranks the most based on the ratio of low pass filter to the total variance, so that its resulting leading modes really tell you the most of the low frequency variability that we are interested in this problem. So I'm going to apply this method to ERA5 reanalysis, don't know when, or 1950, longer period from mid-century to present day. And we focus on DGF only and the cell motion only. And we define this low frequency variability by, well, applying this 15-year low pass filter. And we return totally 5 UFs, accounting for over 70% of the total variance, but results really not that sensitive to the how many UFs returned. But just to give you some examples of how this method works. So this is the leading mode that we apply to, we got using this method to this zonal wind. You can see the spatial patterns feature the strengthness of its westerlies around Antarctica, almost, but of course not perfectly annular. And the time series, the PCs on the left, is still some high frequency variability, but you can see this low frequency variation, especially the trend, the positive trend starting from maybe 70s-ish to 2000-ish. That's widely believed for this trend, positive trend, has pretty consistent with what we thought about the forced trend in the SAM due to ozone depletion. By contrast, just to give you a sense of how this model, how this method works, the last mode gives you this wind anomaly is totally different, like feature more zonally asymmetric features, asymmetric anomalies, and this time series is more dominated by high frequency variability. So from now, we're just going to focus on the top leading 3 modes, both because they are low frequency dominated, and also because the top leading 3 modes can fully reproduce the actual observed wind trend over recent decades. So instead of the SAM index like we showed earlier, next we're going to use these PCs as an analogous or alternative and show ST regressions and the ST reconstructions. So here is the ST regression maps. Both DGF and annual mean SST regress onto that PC time series. And you can see this is to show how SSTs change associated with this mode of wind variability. And you can see along with the wind strengthening, you do see this ST cooling over the large part of the Southern Ocean. And consistent with what we found from just a simple SAM index regression, we see this cooling is most pronounced in DGF and doesn't really show up or persist until the annual mean time scales. So at this time scale, at this step, it's pretty consistent with what we found using just the very traditional SAM index. But eventually, we want to back out the whole time series of SST anomalies and ask how much does it contribute to the total variability of the Southern Ocean SST. So here, combining these PCs and the SST regressions, just to focus on DGF, and then got this SST anomalies associated with PC1 in blue, and also layout this black line is actual observed SST anomalies. And you can see, although this wind mode gives you some SST cooling response, but overall, the variability compared to the actual observed total variability is so small, it's really hard to believe this mode or this mode associated cooling contribute that much to the total variability. And to further show you this contrast or this little contribution, plotting the trend maps, all the trend maps are not perfect, but we're interested in this recent decades, trend over past 40 years over the Southern Ocean. The SST trends of 10 were associated with the PC1. And the top 2 panels are the actual observed SST trends. And you can see, well, although PC1 does contribute to some SST cooling, yeah, you do see the color. The some blue color here shows the cooling trend associated with PC1, mostly strongest in DGF, but much smaller compared to the observed total ST trend. Meaning that this PC1 associated ST contribute little to both the long-term variability and the recent trend. And you may wonder, well, this is just the first mode, it's one of the leading modes. If we sum up all the SST variabilities associated with PC 1, 2, 3, 4, 1, 2, 3, which totally reproduce the regions observed the wind trends, but they're resulting in SST anomalies, well, larger variability than before, but still not as strong as observed. And when I focus on the Southern Ocean SST trend over recent decades, especially in the Pacific sector, where you see the strong cooling trend observation, but the SST trends associated with PC 1, 2, 3, 4, all these together, collectively explain maximum up to 40% of the total observed trend. In DGF, the season where we see the strongest ST response to the wind or to the SAM. And this number can even drop to less than 20% in annual mean, because in annual mean, we don't see much of an ST response to the SAM. So based on this observational analysis, that really tells me that this seasonal or triennial fast time scale SAM or wind modulation of SST doesn't really account for much of the actual multi-decadal long-term SST trends, suggesting that the SAM-induced wind strengthening is unlikely the main cause of the observed multi-decadal Southern Ocean SST trend. Okay. Yeah, so summary, in the first part, I just used very simple SAM index and found that in observation, we do see this ST cooling response to the SAM that acts onto the fast time scales. And surprisingly, models get that pretty well. It's unlike the key reason for model biases in long-term ST trend, because in observation, we actually see this SAM associated or wind associated ST cooling doesn't account for much of the long-term trend. So suggesting that other reasons other than SAM, like Antarctica ice sheet melting or some other internal variability associated with southern ocean convection might be more plausible reasons accounting for this recent observed long-term trends.
So next we will have Andrew Schurer, who's coming to us from Edinburgh. He is in Edinburgh.
Hello. Can you hear me? Can you hear me? Wonderful. Yeah, welcome from Edinburgh. Can I share my screen?
Yeah, I think he can tell us.
I'm going to share, so we need to stop sharing here. Yeah. Okay. All right, sounds good. Yep.
Okay, so can you hear, you can see my slides, you can hear me? Yes?
Yep.
Wonderful, good. Well, then I shall start. Well, yeah, well, hello everyone. Welcome from Edinburgh. It'd be lovely to be with you, but it looks like a fantastic meeting. But unfortunately, I can't be here. Oh, there. So, yeah, I'm going to be talking about some work I've been doing over a number of years, which has been looking at the human influence on tropical precipitation. Yeah, precipitation, as I'm sure everyone at this meeting knows, is controlled by both temperature and circulation. And so, yeah, because of what we've been hearing, circulation is really not particularly robust between models. Various models do different things. It's quite noisy. And this means that the global models are much less consistent in their predictions of rainfall changes in temperature. So different models will predict different things. It's a really quite weak signal-to-noise ratio. And this, of course, means if you want to detect the human influence on precipitation, it's quite problematic. So the work I'll present today has built on about 10 years of different people's work, where they've used a fingerprint of the changes in wet regions, wet and dry regions precipitation in order to really disentangle this. So this is not work that's been inspired by me. This is work that's been going on back now 10 years to at least 2013, and in fact older. So Debbie Paulson looked at this in 2013 and 2017. I was involved in a paper a few years ago, and that produced a figure for the IPCC AR6. So I think hopefully it's of interest to this meeting, because I think it's quite a nice example of how trend analysis can go. We've essentially got the same analysis with the same kind of metric going back 10 years. So it's nice to see how the results have changed through time and whether they've been consistent. Obviously, the observational data set has increased and the models have changed. So a little bit about the metric I'm talking about. So I'm talking about the wet and dry region rainfall. So this is relatively straightforward, but it's worth probably going through this. So we take all the models, and for each model for each month, we look at where the rainfall lies. You look at a distribution. You rank all the grid squares, and here we're looking at just the tropics, so 30 to south to 30 north. So you rank up all the grid cells. In this case, 3,456, 2.5 times 2.5 grid boxes from the driest to the wettest for that month, and you just work out. You just take the mean over all the wettest regions, all the driest. So we define wet and dry regions based on the rank. So we're looking at the third driest regions and the third wettest regions. So that's how we define wet and dry. And so here, this is just one example for one model. And of course, anyway, yes. So for each model, the point is you follow the wet and the dry regions for each model individually for each month. So this isn't a static grid. It's not saying that the same regions get wetter in all models. It's just saying where the models are wet, it gets wetter, and where the models are dry, it gets drier. So this overcomes some of the issues with the models having precipitation in different places and also having different circulation states. So yeah, so this is hopefully quite a nice, robust metric. And just to show, this is just an average of where wet and dry regions are in the models and the observations for the different months, for different seasons. And of course, yeah, there are some biases, but in general, the models do a relatively good job. And here we're just showing you that these are really quite robust changes. So I'm not sure if you can see my mouse, but on the purple on the right is the wettest 10% in all models. So that's getting quite a lot wetter. The trend is positive. On the left, in the red, you've got the driest regions, and they're on average getting drier. And the more wet the region is, the more wetter it's getting. And in addition, it's also interesting to note, although I'm not going to focus on this, that the regions of large-scale descent are getting drier, and the regions of large-scale ascent are getting wetter. And of course, that's part of the picture here. And if we look at the projected changes by the end of the century, these are really nice, robust results. All the models are saying that in all models, wet regions are getting wetter. And so that's really nice. It's a really nice, robust fingerprint that really it's nice. Nice strong signal to noise, and all the models have so consistent behavior. So that's the metric. Results are coming from this paper published a few years ago now in 2020. Yeah, so this is just showing you the time series of this. So we're using CMIP6 models. The top panel is showing you the wet regions, and the bottom panel is showing you the dry regions. So these are the wettest third and the driest third. Model observations here are shown in black, and that's coming from GPCP. So yeah, by eye you can see that the models are for the wet regions are getting wetter, and for the dry regions are getting drier, and the observations kind of follow that. We're using a detection attribution approach here, which is just a linear regression. So the regression factors are shown here. So essentially what we're doing is we're drawing both fingerprints together and seeing what scaling factor for the models is consistent with the observed variability. And you can see that we're getting a positive scaling factor, which is good, and it's significant because it's significantly greater than 0, but it's actually bigger than 1, which means that the models have to be scaled up in order to match the observations. And you can kind of see that by eye. And the uncertainty here kind of takes into account the internal variability that we could expect. So you're looking of course, there's lots of different single force runs in CMIP6, and you can kind of see that the greenhouse. This is what we're seeing is basically greenhouse gases being is predominantly greenhouse gases causing the wettening, and in the wet regions and dry regions. Aerosols are doing some kind of thing. Obviously, there's a reversal in the aerosols. And the volcanoes are causing a drying of the wet regions in following Pinatubo. And you can do a multilinear regression, and you can prove that that it is the anthropogenic, which is really cool. We can detect an anthropogenic effect here. So that's great. And yeah, so that's the nice results. Of course, we're talking about trends here. That's the name of the conference. And fortunately, I've also done this in terms of trends. So this is kind of intuitive. It's kind of the same as before, but just showing it in a slightly different way. Here we've got wet regions. So all four models are in blue. Observations are in black. Grey is just what the controls want to do. So the observed trend in the wet regions is much larger than in the controls, and is vaguely consistent with the models, but very much on the upper end. In the dry regions, the same is true. It's the drying, the observed drying is outside what you expect from control, but it's also outside what you'd expect from the models as well. So the observed observations are showing trends which are which are slightly larger than what you'd expect from any model. So this is kind of the theme of the workshop. This is quite interesting. This suggests that the models maybe getting kind of the false behavior right. They're getting the right sign, but they're actually needing to be scaled up. They're actually significantly not strong enough trends. So that's a nice result. And when we look back at all the results that have gone before from Debbie Paulson's papers, this is exactly what was seen in 2013. So she also detected the influence of anthropogenic, of forced behaviour in this metric, but found that this was much larger than what the models suggest. So the models had to be scaled up. This is also the case in her 2017 paper. Again, the model forcings have to be scaled up in order to meet the observations. And yes, the IPCC also showed this as the results were taken from the paper I've been presenting. So that's really interesting. So yeah, we're definitely quite confident we can detect a forced response in these observations. But what to make of this? I mean, this would suggest that the models are not getting a strong enough trend. And that obviously has large implications for future hydroclimate projections, or at least it could do. So we could, for example, assume that this means that the predicted increase could be larger than the CMIP6 projections if we need to scale everything up. So this leads me to the last part of my talk. So around about the time I saw this meeting being advertised, I'd just done an update. I just ran the update of new GPCP observations, and I think what came out of it was pretty much similar to what Gavin had described about the hiatus. So it's got really quite similar, interesting similarities. So GPCP has been updated. Probably some people know much more about this than me. This is now version 3.2, and we run the analysis, and yes, what happens is that our results are now consistent, which is nice. The scaling factors are still significantly positive, so that's wonderful. It means we're still detecting a forced change, but it's now consistent with 1, which means we don't significantly have to scale up the models anymore. And if you look at the histograms, they now perfectly line up. The wet regions are getting as wet in the models as the observations, and the dry regions are now quite very consistent with the observations. So that's great. So what's happened? 2 things. And again, I think this really relates to what we're seeing in the hiatus. So obviously we've got another 4 years of data. So for the wet regions, what's happened is that the recent period is not as wet. So the wet regions have got a lot. The precipitation in the wet regions has dropped off quite considerably in these final 4 years. So that's brought the trend down in the wet regions quite considerably. So that's interesting. In the dry regions, it's another thing. So we can see here that really what the difference is not coming from the additional years, but it's actually a change in the algorithm of putting GPCP together. So this shows that yes, we are getting different results, and that's coming from 2 reasons: additional data and changes to the observations. So that's that's quite nice to see. A couple more slides. The AMIP, I've done the AMIP through this, and the AMIP does a good job of capturing much of the variability, so that's nice. But does that mean everything's fine? Does that mean we've understood everything? No, of course not. If you look at the variability, so here, if you look at the unexplained variability, so this would be what you'd expect to be from internal variability. In the wet regions, the variability is much larger than one could expect from control variability. And this is shown, this is a time series of residual here, the 2 standard deviations to control by the dotted line. So, and this is broken down by the different, this is wet regions, these are the different control simulations. So the residual is much larger than the control simulations for all but 2 models shown here. So this is suggesting that the variability in this particular metric in the tropics is larger than what the models would like to do for the wet regions. So the wet regions have got much more variability than the models have. And in addition, of course, what I'm showing here is just a simple metric. It's just the wet regions and the dry regions. Tropical rainfall is, of course, much more complicated, and so more work is needed to understand a lot more of that. So that's the end of my talk. Hopefully it was of interest to the meeting. So in summary, we've analysed monthly rainfall for the tropical regions. We define the regions as wet and dry depending on the amount of rainfall in any given month. Model projections show a robust pattern of this, and the observations show a similar pattern. And the updated analysis now shows that the signal is clearly detectable and the magnitude is now consistent with the observations and can be attributed to anthropogenic forcing. So that finishes my talk. Thanks for listening.
So now we have time to have everyone ask all of their questions from the last 5 talks. So why don't we have the speakers come up and sit at our panel here and find them.
Online question, Herb, if you want to unmute and ask that.
Yes, can you hear me?
Yes.
Yes. Thanks for the talk, Andrew. I was wondering if you have had a focus on land areas only, wet and dry, and also how the new GPCP product compares with GPCC over land.
To answer the first question, I haven't specifically, but I know that a lot of this kind of metric doesn't work as well over land. It's much more noisy. Things are very complicated. A lot of people have said that this paradigm works much better over the ocean than land. And to address the second point, I don't actually know yet. I've not looked at this. So no, I don't know how GPCP compares to GPCC. But yes, it would certainly be interesting to look at. And I'm not 100% sure I totally understand. And I'm sure there'll probably be people in the room that know more about this than me, exactly how GPCP has changed over the last in the last iteration.
There was a question earlier from Gavin or Alexey. So there, I didn't read it. Question is, how do you know that the 1 to 25 year response in the abrupt 4 times CO2 runs is forced? It seems short enough that even with the large forcing, there will still be large internal variability. Do we need a large ensemble of abrupt 4 times CO2 runs as well?
25 years in 4 times CO2. We use 7 models. Each model has 3 ensemble members. So it's basically 21 realizations. It's obviously not 100, but it's pretty much forced response. Obviously, you know, if we take 1 sample members, we'll probably see a little bit more smoothing or something, but even taking out some of that model gives you more or less the same pattern. So I think we're sort of marginally getting this mean response, even 25 years, even 7 models in 21 ensemble members. Again, it would be nicer to have 100, but that's what we had.
Okay, I have a question for Alexey. So in describing the oceanic thermostat, you kind of emphasize the zonal context along the equator. However, when you change the winds, you also change the meridional transport of the subtropical cells. So how does that enter? And then related question, how this transient response ends?
Okay, so there are several components. So, the original idea of ocean thermostat was mainly looking at the tropics, Amy Clement's papers, Richard Seeger, McCain. So it's west versus east, right? So it's a strengthening Walker circulation with the warming of the west. The pattern of the thermostat we see in the waters, it has a very strong subtropical component. And we're talking about the southern hemisphere, this region of the coast of South America, where you have strong southeasterly trade winds. And apparently when you apply CO2 forcing, that's the region that gets colder, or at least you see a clearly suppressed
warming in that region. And then and then the equatorial band catches up, and you see a strengthening of a local circulation. So clearly, in the general thermostat, there is this connection between southern subtropics and the equatorial band. So that's the first part of your question. And so wind evaporation feedback, west feedback is probably working somehow connecting this region to the equatorial band. So that's the first part. The second part, the role of subtropical cells. So what we see in the many of these experiments and models is that, again, there are many, it's somewhat model dependent, but I think overall you see a weakening of the subtropical cells. And that weakening of the subtropical cells actually works to erode the thermostat to some extent over this 50, 60-year time frame. It's part of this erosion of the ocean thermostat if it's there. In models when it is not there, well, it doesn't really matter. Yeah. And there was another part about transient, so I think that's, yeah, the part. So we never, in anything what we've done, we haven't seen ocean thermostat persistent for more than like 50, 60, maybe 80 years at most. Ultimately, this eastern equatorial warming pattern wins over. It could be a problem with model biases because, you know, if the ocean thermostat is weak from the very beginning, well, maybe it will take longer time. But yeah, but I don't think ocean thermostat is sufficiently strong, really wins over the response. Ultimately, a couple of decades, 50 years, it has to go to the warming and weaken the water circulation.
Do we have any questions for some of the other speakers? Bill, yeah.
Got a question for Maria. This is more of an observation. It follows on Gavin's talk. The shortwave, it's more of an observation. I'm a little puzzled as to why shortwave is proving to be tricky. I mean, the things that are changing, which are the cryosphere, is spatially distinct from the low cloud feedbacks, which are strike you over the open ocean, are spatially distinct from changes in aerosol load in the northern hemisphere. So, I mean, that problem should at least be spatially disentangleable, if that's a word, even though all those signals are very broadband. And in the infrared, we have the series record overlaps precisely with data from AIRS, so we can tear that problem apart spectrally. I guess I don't understand. I guess I'm puzzled as to why this looks hard, because we have spatial disaggregation on the short wave and spectral disaggregation on the long wave. We'll go a long way toward figuring out what's going wrong between the model ensemble and the observations.
I think it just hasn't been done yet.
Okay.
What I would add to your list is the SST pattern.
Yeah, yes, absolutely.
Or a fourth and link
Sure.
the clouds, and who knows, maybe also the CIs
Right.
might be driven by the aerosols or not. Yeah. No, I think it's a solvable problem. And in the models, we just have to run the right simulations, right? So this is Cirrus map, but nobody has done this. And in the observations, literally, people split between shortwave and longwave, and that's it.
Yeah. Thank you.
Rob?
I have a question for Yue, or two similar questions about whether you've checked a few things, because you talked about it in introduction, how it's the timescales of response. So one thing I was wondering is if you looked at lag times and if that changes your answers about how big of SST noise you can get from the winds. But the other somewhat related question is the way you're regressing things, you're regressing SSTs, which have relatively less noise on a noisy wind variable. Now, so when you have a noisy X variable in a regression, this could lead to problems of regression dilution. So I'm wondering if you've tried switching order of the regression and if that changes the results.
Yeah, good question about the methodology. First, we eventually decided to use zero lag regression, SST onto the SAM or the wind anomalies, because we see the regression maps, the maximum regression really stays in the same season. And well, basically the end of the year is going to go to zero. So if we were to extend that regression the next year, so lag 1, there's no signal. So it seems like the most is a fast response of SST to the SAM. That's why we decided to use this zero lag instead of including all the lag, because all the lag doesn't really give you the SST response to the SAM, fast response. Because in observation, we see this cooling response and consider it as a fast time scale cooling response to the SAM. A second, is that like a swipe of the, okay.
Have you switched the order of the regression to avoid the problem with regression dilution of lots of noise in the wind variable?
Yeah, we haven't tried that. The wind is indeed pretty noisy. That's why we decided to use this approach as a low frequency and also apply this 10 years, 15 years, or 20 years low pass filter, trying to assess this more low frequency variability. But we didn't try this. Yeah.
So is there another question online?
Yes, we have 2, but the first is from Tim Stockdale. You can unmute.
Okay, thank you. It's a question for Andrew. I just wondered, Andrew, if you could clarify the change in the agreement between the trend on the precip with the new GPCP data set. Is that really largely because of changes to the data, or is it that we've got these extra few years that have shown, going in the opposite direction? And if it's because of the last few years, then I guess the question is, the trend over the period we consider might match, but the time evolution might not. And I'm thinking, I guess, in my head that aerosols have been changing as well in recent years in a very different direction to what they were changing before. So might that be part of the story? Do you just want to comment on trend versus time evolution?
Yes, of course. Good question. I think it's complicated in terms of the wet. So I'm not sure I should have, I'm not sure I've changed share my screen again. But it really is I think it is for the wet regions. It really is the last few years that are bringing it down. So it is a case that the trend has changed. So it's a bit like the hiatus. If you do another few years, then some of this goes. So, and I think partly it might be due to the variability in the models not being quite as strong as what the observations is. So it looked like a significant change if you looked at the model variability, but actually, it probably was just natural variability. And, you just need a few more years of data because, of course, we've only got 30 odd years here. We're talking satellite era, so it isn't a lot of data. So sometimes you do need that more to it can change things quite a lot. In terms of the disentangling the aerosol, I mean, it is an interesting question. I think you need a lot more data. The signal to noise is still quite low for this fingerprint. So the aerosol signal is very interesting. If you look at enough model simulations, you can see that it reverses around the 1990s to 2000s, as the aerosols start cooling, particularly in the northern hemisphere, because a lot of this is driven by, interhemispheric difference. So that is an interesting point, but I don't think we could really disentangle the greenhouse gas from the aerosol in using such a short data set. Okay. I should say, though, that the updated GPCP has definitely changed how the rainfall in the dry regions quite considerably. So all the results of the dry region is very much, it does seem to be coming from the difference in the algorithm of the actual observations itself. Hopefully that answers your question.
Good, yes, thank you.
I have a question for you, Ray. I was wondering why you chose to focus on DJF winds. DJF is summer in that region, and that's a very shallow mixed layer. And I think when we're looking at Southern Ocean cooling, it's year-round, or I think it's important to think of the deeper mixed layer time of year. And an older paper I did with a student, Fan, we showed from the COAD's ship data that the zonal winds have a beautiful match to the observed warming and subsequent cooling trends in the Southern Ocean. So I think we have to be really careful that, winds are still absolutely part of the picture for understanding the Southern Ocean. warming and cooling trends. And I think just focused on DJF, to me, didn't sort of look at the bigger picture of, the winter time.
Yeah, good point about, so we're focused on the DGF wind because this is the season where winds have a significant trend, but we do the accounting for SST response in all seasons like DGF regression or AME SST regression or JJ SST regression onto the DGF wind. And we just show that the most strongest ST fast time scale response is really pronounced in the same season and doesn't really persist onto next season or the whole seasons, the whole year. Yeah, I also want to highlight the time series. Like if you plot shorter time period and me, Sam, or wind stress time series and the sun function SSTs, you do see some perfect opposite spikes, meaning that the SAM or wind contribute to some intraannual variability. But as I showed earlier, like if you plot around mean or low frequency variabilities, you can see they really, the phase don't really align with each other. Like the SAM trend of the wind.
So we found they align perfectly. So that's what I'm trying to say. To bring the data back to 1950 from the Polaris winds showed that perfect alignment of up and down. So I think SAM DJF is a good story. I'm not trying to be confrontational. I'm just trying to say we should think broader.
Oh yeah. So like we do see some contribution from this. It's just like eventually we'll quantify this numbers found like relatively smaller than we had expected. It seems like not the whole story of the southern ocean cooling. So probably suggesting other ocean terms like freshwater input or some other non-wind associated cooling might also contribute a large portion of the total trend. We got like DJ at 40% and me like 20%. That seems at least smaller than I had expected reading all this literature.
I wonder if you're looking at the same time periods or not.
We're looking, from 1950, and we can see the winds weaken as the Southern Ocean warms and the winds strengthen as it cools. I think Magdalena had a good follow-up about ocean, fourth ocean model.
Yeah, can you hear me? Hello, can you hear me?
Yes.
Yes, okay. Yes, it's a question for all really, is whether, well, the ocean thermostat is quite intriguing and why some models display it and others not. What is behind that? I was wondering whether anybody knows if the ocean-only simulations display any change when forced with reanalysis winds, display any sign of the ocean thermostat at work, and equally if the AMIP simulations, when the atmosphere model is forced by the observed SSTs, show any signature of increasing of the trade winds.
Yeah, I guess I can answer this. So AMIP simulations, if you force a SST, we do show the strength of the local circulation. That's basically pretty much sure the theme. I know about some of the experiments forcing the ocean by the observed winds, and they do show the cooling pattern more or less. Yeah, so there is a group in France doing that. So I think it's consistent. The problem happens when you actually have a coupled system. If you force the atmosphere by the observed SST, or you force the ocean with observed winds, you more or less get the patterns pretty much. There are some issues, obviously, biases, but overall you do get what's observed.
Yeah, if I can comment on the answer, Alexey, for the ocean, if they are forced with observed winds, the cooling pattern is not enough, I think, proof of evidence, because that cooling pattern will be inherited by the constraint to 2-meter temperature. That's all the ocean. When we force the ocean, there is a constraint. So one will need to check changes in the circulation, I think. But thank you for the answer. Yeah.
Yeah, that's true. But I just I haven't seen what was done
or actually subsurface fields. Yeah.
Thank you.
John?
Okay, thanks. Great talks. The question is for Maria. So while I was listening to the talk, it reminded me of a conversation with Manabi 5 or 6 years ago. Back then I asked him, well, how do you think your model for projection? He put out these plots. It's more like Minecraft, very close resolution. Model prediction made in around 1990s. If you, well, we have this pattern, we with observe trend, that pattern we also trend. So I guess in the end, my mind was wondering how good is good for our scientists and for stakeholders.
Depends what you want, right? If you want global mean surface temperature, you are good.
Yeah, he also look at patterns. So like you look at the patterns, everything very carefully. I just
What of the pattern do we want to be right?
Yeah.
Totally, yeah, fair question. I don't think we need the full pattern. So this is actually, I didn't show this, but we get this out of these green structure sensitivity simulations, is we know where the atmosphere is very sensitive to the SST pattern. So in principle, I showed one tiny little map of this. It's brought from these simulations. It's broadly the West Pacific, subtropical, East Pacific. That's about it. So in principle, we don't need to get the full picture right to get the atmosphere right. However, okay, this is a lot. We are trying to create these Jacobian sensitivities now with convolutional neural networks based on only data, like model output, not forcing the model, and they look very different, much more fine-grained. So I guess the answer is that we don't know the full answer yet, but it is for sure in the tropics, and you don't need it in every single grid point right there. Patterns. Does this answer your question?
Yeah, that's a great answer. Thanks a lot.
So do we need to move on? Okay. So I think we'll just have to save, generated a lot of discussion, but we'll continue that in the breakouts and we'll have some other discussion points later. So the next thing on the agenda, Alyssa, are you going to register? Okay, is the virtual posters. So we'll have a half-hour presentations before lunch at 12:30. So
Thank our speakers again.
yeah, let's think.
Perfect. Okay. Shall I go for it? Yeah. So hi everyone. My name is Matt Patterson. I'm based at the University of Oxford. And so this work that my poster is based on concerns seasonal predictions of the European summer of 2022 and the connection between these predictions and jet stream trends. So the European summer of 2022 was marked by extreme heat and drought, with the UK, for instance, seeing 40 degrees Celsius for the first time, rivers across Europe at record low levels, and wildfires prevalent across Portugal, Spain, and France. And we find that this season was surprisingly well predicted in ECMWF's System 5, and a lot of that sort of warm anomalies and that dry conditions were driven by northward shifted jet stream, which contributed to those anomalies. But we also find that, let me just change slides. We also find that differences between jet stream trends in the model and in the observations raised a lot of interesting questions, because the model jet trend contributed a lot to the prediction, but gave the right answer for the wrong reasons. So the top figure shows an attribution of the model prediction to different drivers. So for instance, you can see that a sort of northward shift of the jets due to greenhouse gas driving contributed more to that jet stream prediction than La Nina did, for instance. However, this trend is at odds with the observed southward trend over that same period, as you can see in this bottom panel here. So it was in effect quite fortuitous for that year that the incorrect trend coincided with a northward shifted jet. So it was sort of by chance. Now, overall, this suggests that erroneous atmospheric circulation trends can be key sources of error in seasonal predictions, but we don't really understand the observed summer North Atlantic trend, whether this is something that's driven by greenhouse gases or aerosols, or even if it's just internal variability responding to SSTs. So we really need to do some work to understand what it is that's driving this summer southward jet trend in order to see what the model isn't capturing. So thanks very much. If you're interested in finding out more, do get in touch. I've left my email in the top right, or come and see my picture. Thank you.
Okay, so hi everyone. I'm Sanjeev Kumar from Auburn University. I wanted to shift the gear a little bit and take you to your neighborhood, like where either yourself or maybe your neighbor is asking you, like, there is a flood trend and can I attribute it to the climate change? And answer is no, or at least based on the analysis that we did. We looked into around 4,000 of the USGS gauging station, and what we find, there are more of the decreasing trend than the increasing trend that is shown in the top panel. Then we went ahead and for each of these 4,000 watershed, we extracted their watershed attributes, including that there are 88,509 dams in this conterminous United States. We assigned each of those dams to the watershed and then explore what factor may be driving. And what we found that two main factors that is driving these observed flood trend. First is urbanization. You see the Chicago area, New York area, Houston area, or California. Those are showing the increasing trend. The second most important factor is water management, that the water is stored behind dam and reservoir, and that is driving most of the decreasing trend. So when you look into the climate model, like in this case, it's the CSM2 large ensemble, what you find that when we consider all the trend, climate model is not able to capture the trend. Whereas if you only look into the reference site, that is very minor fraction, 620 out of those 4,000, climate model is able to capture the trend. So why does the climate model does not capture the observed trend? It is because of the process deficiency. In this particular case, it is water management and urban expansion. I hope I am in time.
Okay. Yeah, hi, I'm Alan. I'm a PhD student at Penn State working with Shuker Lee. My poster is about predicting the tropical Pacific using the DJF climatological cooling rate. This motivation is from, as we've seen before, that the tropical Pacific response is not captured well, and there's many theories for both strengthening and weakening of the zonal gradient. So we took a really simplified approach, and we've asked the question of, given a uniform forcing and using the first principles of thermodynamics, what's the response retrieved, shown with this simple equation, where this gamma is the climatological cooling rate. And how we've defined this is just from upward long wave radiation and then the sensible and latent heat flux related to Q saturation and the SST. And what I'm showing in the bottom left is basically the key figure is that from gamma, we've received a La Nina like change where we get this cooling in the central Pacific that aligns somewhat well with the observed change with the tropical mean removed. And this result is from gamma, but more importantly from gamma, it's decided by climatological wind stress. One caveat is that we don't really include the feedbacks of like cloud radiative forcing and stuff. So that's something we have to keep in mind. And we've also analyzed precipitation. And from the method, we kind of get like a warmer gets wetter pattern. But yes, please stop by my poster if you're interested or contact me at my email up in the top left. Thanks.
Okay, I'm going to go ahead.
Hi, so I'm Emily. I'm from the University of Oxford, and today I'll be presenting results from a study where we estimate tropical cloud feedbacks using observed multi-decadal trends. This is novel because previous work used shorter satellite datasets and so calculated feedbacks from short-term variability. Here we instead use a dataset called DeepSea, which combines URBI and series data to provide all sky top of atmosphere radiation from 1985 to 2020. We combine this with ERA 5 clear sky radiation to calculate the cloud radiative effect, or CRE. And then to calculate cloud feedbacks, we calculate trends in CRE and in tropical mean surface temperature, and then divide the trend in CRE by the temperature trend. So in the tropical mean, we find a neutral net feedback, but as shown in the plots in bottom right, there are large regional long wave and short wave feedbacks. We've explored the drivers of these feedbacks, and we find important roles for the Hadley and for the Walker cells, and I discuss this further in the poster, so please do check it out. But we also looked at how feedback estimates change depending on the method you use and the implications of this. So firstly, I compare trend-derived and variability-derived feedbacks. So to estimate feedbacks from variability, you directly regress cloud radiative effect against tropical mean surface temperature. And you can see from the plots that I've added that clouds don't respond in the same way on the two timescales. And this is partly because the pattern of surface warming is different, but it's also because other elements of the climate system, which also influence clouds, vary differently with temperature on the two timescales. So an example of this is tropical circulation. Again, this influences the feedbacks for variability timescales, but the circulation changes are now dominated by end zone. And the implication of this result, and maybe I'm preaching to the choir here, is that you can't directly use feedbacks from observed variability to evaluate how clouds respond to anthropogenic forcing in models. Instead, a more nuanced approach is needed. And then lastly, I wanted to turn to a slightly different topic, which is the effect of replacing the deep sea all sky top of atmosphere radiation with ERA 5. And here the plots show the difference between deep sea and ERA 5. And you can see that there are, again, very big differences. And to my mind, deep sea in this case is much more trustworthy than ERA 5 because ERA 5 doesn't assimilate top of atmosphere fluxes, and instead cloud radiative effects come from the model parameterization. So the reason why I think this is interesting is that cloud radiative effects can also influence circulation because they modify the energy present in their atmospheric column. So it's possible that if ERA 5 has biases in the cloud feedbacks, this could be causing biases in the circulation trends too. So thank you, and please reach out if you have any questions or would like to discuss further.
Okay, hi. I'll be talking, my poster is about thermodynamic trends retrieved from 20 years of AIRS observations. My name is Sergio de Souza Machado. I work with Larrabee Stroh at UMBC. Larrabee, oops, can you go back? Larrabee is one of the the first slide. Larrabee is one of the NASA Sounder science team leaders. And you all know I think most of you all know our third author, Ryan Kramer. Next slide. Okay, since September 2002, there have been a number of new generation hyperspectral sounders that have been launched by NOAA and by NASA. And basically what Larrabee has been doing, he's been stitching together the records from AIRS onto CRIS, so you can smoothly, they actually overlap in time. CRIS went up in 2012, and AIRS went up in 2002, and it's still going strong. So we've been monitoring the radiances measured by these guys. We have one spectral response function that is smoothly going to tie together the entire 40-year record from these instruments. So you will have access to a really good observational database. These instruments have high spectral resolution, so lots of sounding, and they are extraordinarily stable. The panels below that just show, on the top panel is globally averaged AIRS observations in brightness temperature, And what y'all are interested in is the bottom panel, which is how these brightness temperatures have changed over the last 20 years. So if you look at the window region, the surface temperatures have changed globally on average by about 0.02 Kelvin per year. If you look slightly to the left at about 800 wave numbers, between 600 and 800, you can see CO2 increases and temperature increases. If you go to the right at about 1500 wave numbers, you see the water vapor feedback. Next slide. What we differ from the other people is we use only radiance strands, because if you take the radiances and try to invert them to get temperature and water vapor, you're going to get a lot of errors creeping in from your first gas or from clouds. We are working purely in terms of radiances. So we take the radiances, we form the anomaly, and then we form the trend, the radiance trend, spectral trend, and then we do a one-step retrieval to get surface temperature trends, atmospheric temperature trends, and water vapor temperature trends. And we think, at least in temperature, everybody agrees when you compare to numerical weather prediction models or as level 3 data. But when you look at the water vapor trends, you'll find that there are differences. And we believe we are doing better because we are purely going right off the observations rather than just, introducing uncertainties as we do the retrievals. So the plot below there, the panel shows the surface temperature trends. On the upper left is our retrieval, and then the other ones are by numerical weather prediction models, GISS, and also by the AS level 3 people. You can see the cooling in the tropical East Pacific. You can see some cooling in the Southern Ocean, and you can also see differences from all these guys. For instance, if you look at India, there's a lot of cooling in the daytime from my analysis, which is not picked up by some of the models. Last slide, please. And so we've gone from these retrieved thermodynamic trends, and we've been able to compute clear sky long wave feedbacks. So you can see our surface temperature trends there in red. They are 0.02 Kelvin per year. They compare pretty well with the other models. And then I've also been able to compute clear sky long wave feedbacks. And we differ from example series because we can break apart all this into lapse rate feedback or water vapor feedbacks. Series is a broadband measurement, and it cannot do that. Well, we can break apart all this. So everything is in our poster. Feel free to contact me at sergio@umbc.edu. And Ryan Kramer is going to be at the meeting tomorrow and Friday as well, if you have questions. Thank you.
A lot more discussion before going for lunch, because there were some questions that we didn't get to in the last session. If the presenters are willing to continue to answer more questions, everyone's still here. You don't have to come up, but I'll read out some of these questions. There's one from Amy Clement for Alexey. Were there any notable differences between the OT and the non-OT models, which might give us some clues as to what's going on?
Okay, so the question is, it's a good question. We didn't do a very careful analysis with CMIP6 models, what exactly separate in terms of physics, the OT and ET group. But going back to our experiments with two versions of CSM1, one version high resolution showing a stronger OT, another version of coarser resolution showing a weaker OT. So the resolution is one of the factors, but how exactly it works, it was not very clear. So we looked at the structure of the thermocline. And in our case, so in the coarser version, the thermocline was pretty diffused. And so if you look at the thermal structure, there was not a huge difference between east and west in terms of thermocline structure. So in the high resolution version, there was really different regime in the west and the east because of sharp thermocline. So the west working more like a mixed layer, so pure radiative balance, east working as upwelling region. And then we got a stronger ocean thermostat. So in my mind, you really need to have this contrast in physics between west and east to generate a strong thermostat. If a model has a strong cold bias, a cold time extending and extending all the way to the west, it's probably not going to create a strong thermostat. But when you have this contrast, it's very important. How models create this contrast, it's a different question. And I cannot really answer what exactly you need. We actually tried to answer to the question, one of the questions, what would you do? What should you do with the model to strengthen the ocean thermostat? And we couldn't really find a good answer. So that's sort of a long answer to a short question.
Well, I think we'll come back to resolution. Right. So, foreshadowing. Love you.
I had a question for Steve Po-Chedley. Since we have more time, whether you want to expand on, I think one of your last points that like you have this beautiful analysis that explains a lot, and then the new data set comes along, pulls it away again, so kind of the opposite of Andrew Schurer's talk. Do you have thoughts on where this is coming from? You waiting for the NOAA version 6 update to come back?
Yeah, so there's one correction that all the data sets have to make to account for diurnal drift. And this is where the satellite measurement time slowly drifts from, say, 2 p.m. to 8 p.m. over the course of its lifetime. And the record's composed of 15 satellites, so they're all drifting in slightly different directions. And the diurnal drift correction can be an order of magnitude larger than the trend you're trying to measure itself. And it's also correlated with other corrections. And so it's very difficult to make this correction independent of the other corrections you have to make. And so I think the takeaway is that this is really uncertain until you have a better way of isolating these corrections. And also, we don't measure the diurnal cycle of the troposphere, so we don't exactly know what correction to apply. That diurnal signal comes from models, and so then you subtract out the model-based diurnal cycle. They bounce around the trends all the time. They half and double and increase or decrease by more than the uncertainty that's applied to the data set.
Could I ask you a quick follow-up on that, please? Sorry. Why is the uncertainty so small on the MSU measurements then? If you know.
Well, a lot of the groups don't put uncertainty bounds on the data. Carl Mears did a really thorough job in 2011. He did a Monte Carlo analysis where he applied different corrections that he could plausibly come up with. But there's also decisions that humans have to make, and these have not been included in the data set. So there's one issue where this MSU satellite overlaps with an advanced MSU satellite. They give very different trends, and nobody knows why that is. There's no physical mechanism that you can come up with. So some people trust the AMSU trend, which gives less warming. Some people trust the MSU trend, which gives a lot more warming. Some people split the difference and take the average. And that, these kind of structural uncertainties and decisions that people make are not reflected in the uncertainty of the current data set. So the structural uncertainty really comes from the differences between different data sets.
A more general question about the spectral biases, I guess for all the speakers. I think that we all kind of learned both with the MSU and the precipitation, as well as series and surface temperature, is that there are these really large structural biases, but we tend to take the most recent data set and then chase any biases that are out there. So what should we, if we know that the structural biases are there, but they're poorly quantified, how do we even go about? It seems like we're kind of chasing after bright things, and then the data set shifts and we decide where to look. So how should we proceed knowing that there's uncertainty without actually knowing it?
We'll answer that in the breakout tomorrow. Does any of the speakers have any thoughts?
Yeah, I had one question for Maria, but in fact is very much related with this thermostat discussion that was taken. and it was, please correct me if I am wrong, because I am not working with CMIP modeling, but if, to my knowledge, they don't assimilate observations. I'm not if I'm correct. But I wonder if with the changes in the trends that Maria indicated that they were not correct in time, in general, but they were improving towards the last part of the record, towards the 2000. And Gavin mentioned that one exercise that is done is that, well, modeling is improved through the validation with, again, some observational products. So I was wondering if this improving of the trends were related with the fact that since the 2000s we have the Argo floats, for example, and so the ocean interior maybe is more properly reproduced in the models. So I don't know if this is a possibility.
Yeah, what is the information? So they are not assimilation, the CMIP models do not assimilate observations.
Yeah.
It's not the better observations. I think so, and they do, the trends in the East Pacific mostly do get better in the last 20 years, but I don't think we can say whether that's by chance or not.
Okay.
Like it could just be a PDO signal. It could be the forced response overpowering the thermostat, which we saw already in the 80s. It could be that the ocean thermostat is at full force and this is just a variability. I really don't think we know. There will be an ECS online symposium dedicated discussion just on this question.
So there was a question in the chat a little bit ago from Jerry Meadhall.
Yeah, so this is a question for Yue and Alexey, that you both showed the Southern Ocean cooling trends and the Eastern Tropical Pacific trends. I'm just wondering, is it possible that there could be teleconnections between them? Well, from the Southern Ocean to the tropics that is contributing to the tropical SSE trends.
That was my question to Alex during the break.
So I guess I can answer this. So there is a clear connection between the Southern Ocean cooling and the part of the thermostat in the subtropics, sort of this off the coast of South America. In the way and several other people, Sarah Can, they did this, trying to impose cooling in the Southern Ocean and see how the signals spread to the north. And what they see, depending on where you put the cooling, you can cool part of the subtropics. If you put the cooling close enough, you can actually cool the equatorial region as well. But the problem, if you actually, and this is from Sarah Kempe, if you force a model with observations, so running a couple of models with nudging SST in the Southern Ocean to the observations, you will see the effect of the cooling in the subtropics, but it doesn't penetrate towards the equatorial band. So in short, there is a clear connection, but it seems like this connection is not sufficient to explain strengthening of Walker circulation and the signal along the equator.
I think that was led by Hanjun Kim, who's over there.
It's a pacemaker.
Sorry.
Pacemaker, yeah,
It
pacemaker.
does get to the equator.
It does,
It's
but
not
it's-
as strength as observed, but it does have cooling on the.
Well, but it's really
Did it depend on the version of CS?
Yeah, CSM2.
Yeah.
I guess the equator, but it doesn't affect Walker, so.
Can I,
The last word.
can I just add one more thought on that? Like personally, when I saw that Southern Ocean cooling does not penetrate into the like Equatorial Pacific in that CSM2 pacemaker experiment, I feel like maybe resolution matters because like if the high topography of the Southern America is really like well represented, maybe I think the teleconnection would be different. But
it is possible. It is possible. But again, discussing this the importance of Southern Ocean. So when we did the separation, ocean thermostat and Eastern Pacific warming models, they all have Southern Ocean cooling. But it didn't matter. But some of them have a strong thermostat and other not. And you can see how much the connection is just weak in some models, strong in other models. So that's sort of consistent with what you mentioned. It could be the strength of a connection can vary from one model to the next. But nevertheless, I think it's just a part of the story. Southern Ocean, I think the clear signal is in the subtropics. Yeah, so that's my opinion.
Yeah, lunchtime. So don't forget the posters are immediately.
Hello, I'm Robin Wilson. I'll be chairing the next session, which is a continuation of the trends in the Maine state. And the first presentation, it's an invited talk by Rei Chemke.
Thank you. I'd like to thank the organizing committee for the invitation and for organizing this very important workshop. And further request, I'm going to give an overview of how climate models capture recent changes in the landscape. Now, I won't be able, of course, to go over all of the landscape metrics, so I have to choose some, and I focused on some of the most canonical ones and also the one that have some interesting story in this subject of model observation comparison. And I will start with the tropics, show you some results about the expansion of the Deser, its weakening, and the strengthening of the water circulation. Then we're going to move to the exotropics. First, Northern Hemisphere, we're going to look at the weakening of summer circulation, both the jet stream and stormflex. And then in wintertime, we're going to zoom in over the North Atlantic and we look at the intensification of the jet stream. Moving to the Southern Hemisphere, starting again from summer, we're going to look at the forward shift of the flow, and finally the intensification of winter storm. And just to give you the bottom line conclusion, I put smiley faces next to each one. Green one, the happy one is where we have an agreement between models and observation, and we have this. The sad ones, the red ones are where we don't have an agreement. This is the ones that we have. So the red ones are the ones that we don't have an agreement. You see that we have approximately half of the metrics, and the orange ones are the ones that we used to not have an agreement, but recently we are converging towards an agreement. So I'm going to put some more focus on these ones because I think we can learn a great deal from these examples of how we can maybe go about the rest of the red ones also to become orange. And the reason they are not green is because we need to wait more years to ensure that this is robust. We need to see that the next generation of climate models show the same thing, the next observational products and so on. Okay, but overall you see that the picture is not that great. There are too many examples that we see this discrepancy between models and observations. And this joins the overall kind of conclusion that you can see throughout the latest IPCC report that we have low confidence in how the flow actually changed in recent decades. And for the atmospheric flow, this discrepancy between models and observations, we can think of two main reasons. One is that unlike thermodynamic metrics, we don't have observed wind record, which is continuous in time and space, that would have allowed us to calculate all of these metrics. And instead, we heavily rely on reanalysis products. And as you all know, reanalysis are this hybrid animal of models and observations, so they are also prone to model errors or errors in the assimilation procedure. So not necessarily if we have a discrepancy between models and reanalysis, it automatically means that the models are doing something wrong. And I'll show you indeed a few examples where the reanalysis actually have some biases. And the second thing that was also discussed today is, of course, if we don't adequately represent the physics of what we are looking at in models, also with the forcing our bias, and I'll show you an example of that. And it comes down to what Clara discussed. Do we have biases in the force response or in the internal variability? I'll show you an example. And one of the implications of this disagreement is that we don't know how confident we are in climate projection. This is really, for me, it's the biggest issue here. Okay, so let's just dive in. I'm starting with the tropics. Most of the comparison for large-scale flow tropical metrics started in the early 2000s, and in most of them they found some discrepancy between models and observations. This is about the hadicel width, or the expansion of the circulation and the expansion of the tropics. The figure on the bottom is taken from Johansen and Fu 2009. You see here the 79 to 2002 trends in the width of the circulation. So these are shifting degrees per 25 years. You have here two different metrics for the hadicel width. One is using the stream function on the left and outgoing long wave radiation on the right. You have your observations in both of them. And it is compared to a set of SIMP3 simulation. And what I want you to take from this figure is that the observed trend are outside of the historical SIMP3 runs, and the conclusions back then were that climate models underestimate the rate of tropical expansion. Okay? And what this community did since then, mostly over the past decade, is several things in order to diminish this discrepancy. And two of those things were, one is that they narrowed down the amount of metrics being used to define the hadicel width, because many of these metrics, including outgoing long wave radiation, is not really consistent, physically consistent with the actual circulation. And the second thing is that they found that in the early generation of reanalysis, the one that were used here, there were biases in mass conservation that resulted in some of these larger trends. So how this figure looks today, this is taken from Grice and Davis 2020. You see the 79 to 2008 trends. Again, the expansion of the circulation now, it's degrees latitudes per decade. You have your CMIP 5 and CMIP 6. So the black is 5, the red is 6. The trends in CMIP 5 and CMIP 6 is very similar to what we also saw in CMIP 3. So the trends in model did not change across the model generation. But reanalysis, you can see that the blue symbols here are well within the model spread. And it was improved just because of what I just mentioned. You can also see this blue square here. This is era interim, and this triangle is era 5. So you can see also the difference in the different generation of reanalysis. So this is an example of how it seems that actually the trends in reanalysis were biased in the early 2000s, and using our physical understanding of the system, this community was able to kind of diminish part of this discrepancy. Moving to the next metric, which is the strength of the hadicel. So this figure is taken from a paper that I did with Lorenzo Bombani a few years ago. What you see here is the 79 to 2017 trends in the hadicel strength across different CMIP 5 models in blue. So each blue bar is a different CMIP 5 model. You can see that most models simulate a weakening of the circulation. This is also what we expect to occur in coming decades. And the green bars are 5 different reanalyses that actually show a strengthening of the circulation. So models and reanalysis show opposite changes. And Lorenzo and I did some analysis on that, and we concluded actually that this strengthening seems to be artificial. But the problem again goes down to the fact that we don't have an observed wind record. We don't know which one is right and which one is wrong. So what I did next is this, I collaborated with Jan Yuval, and what we want to do is, although we don't have observations of winds, we do have a lot of observations of surface variables, right? So what we want to do is to link the strength of the circulation to some surface variable that we have observation of, and use it to constrain the circulation. That's the general idea. So we started from the momentum equation, you do simple algebra, and we got to this link. On the left is the strength of the circulation, and on the right you have some function of sea level pressure. And if this link actually holds, then we can use measurements of sea level pressure, calculate this function, and constrain the left-hand side, the hadicel strength. So this is what you see on the right. The y-axis is the recent trends in the hadicel strength, and it is plotted against the recent trends in this function of sea level pressure across CMIP 5, CMIP 6 models. So each red dot is a different model. And you see there's a nice linear relationship between these two, as this balance by this equation predicts. And now we can put our estimate of this function on the x-axis from observations. This is the vertical blue line with some uncertainty. And we basically do an emergent constraint analysis. We exploit this physically based linear relationship, which gives us this horizontal black line with some constraint on the y-axis. So you see negative value. We have a weakening of the circulation, consistent with what we see in models, opposite to what we see in reanalysis. And most models are within this uncertainty of this constraint. So again, another example of how reanalysis seems to be biased. Models seem to capture the correct sign of change. And using our physical understanding of the system, and I'm iterating this, and I will keep doing that, I think it's an important point. We can diminish this discrepancy that we see in models and observation-based or observations. Okay, so the last metric for the tropic, this was already discussed today, is the water circulation strength. Again, this is taken from Mills et al. 2022. You see the recent trends in the Walker cell strength across different CMIP6 single model large ensembles. So each violin plot is a different single model ensemble. The different dots are the different members in each ensemble. So overall, you see that the forced responses of a weakening in recent decades. And these two orange symbols and the horizontal black lines are the observed trends. And you can see that they show actually a strengthening, and not many members are able to capture this strengthening. And this is still an ongoing debate. Some people argue that we have biases in the forced response, that this forced weakening is too strong. Some argue that actually the biases is that the internal variability in the models is not large enough. And just to show you that, I'm showing this figure on the bottom. It's taken from Vecchi et al. 2006, one of the first papers to compare trends in the Walker circulation in models and observations. You see here the evolution of the Walker cell strength since the observed one, since 1850 to present day. You see the strengthening here. This is what the debate is about, this intensification here in observation, where models show the weakening. But you can see also the large variability of this metric. So it's conceivable that if models are not adequately simulate this variability, then they might as well fail to capture the strengthening. Okay. So I'm moving to the exotropics now, and I'm starting with the summer circulation. This is taken from Kalmo et al. 2015. What you see here on the y-axis is the future changes in percentage in storm's intensity, measured using the eddy kinetic energy, plotted against the future changes, also in percentage, of the jet stream, northern hemisphere summer. And each symbol here is a different CM5 model. Except for this symbol here that's surrounded by the pink line, this is actually the changes in percentage from reanalysis. So what I want you to take from this figure is that the recent changes as we see in reanalysis is projected to occur in models by the end of the century. The recent changes are within the distribution of future changes in models. So it suggests that CMIP5 models underestimate the recent weakening of the flow. So what happens in CMIP6? This has actually been improved. This is taken from Dong et al. 2022. Similar, plus you can see in Tim's Wooling paper from last year, you see here the observed trend in the zonal wind from 5 different reanalyses compared to trends in CMIP6 simulation. You can see that they sit well within the model spread. Similar thing we can see for the stormplex. On the right, this is taken from the work that I'm doing with him. You see here the recent trends in the stormplex intensity. The orange one is the distribution across CMIP6 models. The blue is the distribution across CMIP5 models. And the vertical black line is the reanalysis trend. And you can see that it sits well within the CMIP6 ensemble, but at the edge of the CMIP5. So CMIP6 model seems to do a better job in capturing the recent circulation weakening. There are, of course, a few models in CMIP5 that are able to capture the reanalysis trend, and this was also noted in Kang et al. 2023. You see here the trends in reanalysis of the stormplex weakening, and this is a single model ensemble for one of these models, and you can see there are a few members that are able to capture. But overall, you see that the multimodal mean is different between CMIP5 and CMIP6. Most CMIP6 models are able to capture the observed, the reanalysis trend, while most CMIP5 models do not. And why this is happening? So we can think of two possible reasons. One, it could be that there are different model configuration between CMIP5 and CMIP6, and the other one could be that different historical forcings. And to elucidate that, we use a set of simulation done here in NCAR, and Clara mentioned that. What you see here are the trends in the stormplex over recent decades in CSM1. You see this small weakening. And then this is in CSM2 in orange, and you can see a much larger weakening, similar to what we saw in CMIP5 and 6. In CM6, we have a stronger weakening that is more closely to the reanalysis. And then this is the trend in stormplex intensity in CSM2, but it's integrated with CMIP5 forcing. So the same model configuration, but the older forcing. And you can see that once you do that, you get this reduced stormplex trend. So this suggests that the different forcing in CM5 and CM6 could explain why CM5 models show a reduced stormplex weakening relative to reanalysis. And we did further examination and won't go into it, and we find that this is mostly coming from biomass burning emission in CM5 and CM6, and I'll be happy to discuss this later. Okay, so this was summer in Northern Hemisphere. I'm not going to move to winter time. I'm focusing on the jet stream in the North Atlantic, and this is a work done by Blackport and Fife in 2022. You see here the trends on the y-axis in the jet stream since 1951, but ending at different years. Okay, so the black line is the reanalysis 05, and the blue is the distribution across CMIP6 models. And you can see that since the 90s, the models are not doing well in capturing the trends of the jet stream. And actually, by 2020, out of the single simulation analyzed here, out of the 303 actually, is able to capture the reanalysis thread. And they offer a different explanation. None of them seems to found to be robust, including biases in warming patterns, internal variability, biases in the jet latitude. We did found some interesting impact of that. This is the same analysis only done for Southern Europe precipitation. We have here multiple black lines now because you don't have only reanalysis but also GPCP. But you see the same picture that the reanalysis or observed trends are really at the edge of the model distribution. Okay, so this was Northern Hemisphere. I'm moving to the Southern Hemisphere now, and again starting for summer. This is the example where we have an agreement between models and observation. It's regarding the portable shift of the flow. This is taken from Chen and Hal 2007. You see here the evolution of the jet latitude. The red line is the reanalysis, era 40, and the light blue line is the mean of the GFDL CM2 5-member ensemble. The shading is the range across the members, and you can see that they nicely capture the overall pole shift of the jet stream in recent decades. And also you can see that when you look at the spatial pattern of this trend. So this is the trend in air quality plotted as a function of pressure and latitude. You see the intensification around latitude 60 here. And this is in the mean, in the ensemble mean, similar pattern modes. And the storm techs are doing also similar things. So this is analysis that I did. You see here the distribution, the gray bar, the distribution across CMIP6 models in the latitude of the storm techs trends. This is per degrees per decade. And the vertical black line is the multimodal mean, and the blue line are reanalysis, and they sit well within the model distribution. So this is actually a good example of where we have an agreement. And finally, I'm moving to the winter time. This is a work that we did a few years ago. You see here the evolution of the storm's intensity over the 20th and 21st century. The black line is the CMIP6 mean, the gray are individual models, and you see this intensification in recent and coming decades. The blue line is the mean of different reanalysis, and actually showing a much stronger intensification than what we see in models. This intensification is only projected to occur in models by the end of the century. So CM6 seems to underestimate this intensification rate. And we can quantify this by doing a linear regression over recent decades. So the blue bar is the trend over recent decades in reanalysis. The gray is in CM6 models, and the individual dots are, the black dots are the individual trends from reanalysis and models, and you can see that this is really, they're not well capturing the reanalysis trend. And to understand where this is coming from, we basically did the hydrodynamic instability. You see here the result of that. So the y-axis here is the trends in storm text intensity plotted against the trends in this hydrodynamic instability metric across reanalysis in black dots, and CMIP6, this is the two-dimensional PDF here. And you see there's a nice correlation between those two, suggesting that since what's actually affecting this instability metric is the meridian structure of the jet stream. So we concluded that we have larger trends in reanalysis relative to models. Those models are not simulating similarly the changes in the meridian structure of the jet stream. And I think this is a good starting point to resolve this issue. Okay, so I will summarize. I will say that first we find that approximately half of these metrics are not well captured in models. There are many. There were more examples where we have this discrepancy, but the community was able to kind of resolve that. And this was done first by improving our physical understanding. I think this is a very important point to make. We have to exploit our physical understanding of the system in order to diminish this discrepancy that we found. It helped us to to find the source of the model observation discrepancy, to constrain the flow using observations, and also in cases where we have an agreement between models and observations, as we saw for the polar shift of the circulation, we want to understand why we have this agreement and to preserve it for the next generation of climate models. And another thing that helps us to diminish this is conducting more targeted numerical simulation, as done here, for example, in NCAR. And I think these joint efforts could help us move forward. And it's important to, prior to any analysis, to validate the physical consistency of both our models and reanalysis, because both are prone to errors. And by validating the physical consistency, meaning trying to compare them to some observations that we do have and see if they are consistent. And that's it. Thank you.
Red smile in his presentation. So as we just saw, Southern Hemisphere winter storm tracks is strengthening over the last 4 decades, and reanalysis seem to fall outside of the model trend distribution. So the figure here is from Rei's paper, where the trends in 3 reanalysis shown in blue is far larger than the trends shown in the models, which are shown in gray and green bars. And similar analysis for the winter storm track trends in Shaw et al. 2022 shows that this issue has persisted through generations of climate models, indicating an reanalysis model trend discrepancy in the Southern Hemisphere winter storm tracks. So as Gavin nicely laid out this morning, we'd like to understand this discrepancy in these 3 categories. First, whether the observation, how the observational uncertainty impacts this discrepancy. Second, how the comparison impacts this discrepancy. And also third, how the model errors are impacting this discrepancy. So I'd like to first focus on the impact of observational uncertainty. So storminess in the observation has to be quantified through reanalysis data sets. And reanalysis data sets can have large uncertainty, especially in the Southern Hemisphere where ground-based observations are scarce. So compared to previous analysis, we tried adding more reanalysis data sets to account for this issue. And we analyzed the trends in 6 reanalysis data sets. And so the figure here is a similar replication of Rei's figure showing trends of wintertime eddy kinetic energy in individual models and reanalysis in diamonds. And they are filled when they're statistically significant. So first thing we can notice is there is a large spread in reanalysis trends, almost as large as the model trends. So some of the reanalysis are clearly outside the model trend distribution, whereas some models are inside the model trend distribution and are statistically insignificant. So to evaluate the reanalysis model trend discrepancy with this large spread of reanalysis trend, we use a rank metric, which gives individual reanalysis a rank within the model trend distribution. And then we average those ranks to quantify where the reanalysis sits on average within the model trend distribution. So the resulting average rank is 3% for the CMIP6 models, and it's 22% for the AMIP6 models. And with this average rank, we express the likeliness of reanalysis model trend discrepancy loosely following the IPCC language. So when the average rank is smaller than 5% or larger than 95%, we say a discrepancy is very likely. And when the average rank is between 5 to 20 or 80 to 95, we'll say the discrepancy is likely. And the other cases where average rank is between 20 to 80, we'll say the discrepancy is unlikely. So according to this, a discrepancy is very likely for the CMIP6 models, and it is unlikely for the AMIP6 models. And then we will move on and evaluate the importance of comparison. So to ensure that fair comparison is made, we use more model simulation to capture broader spectrum of structural and internal variability. And also, we made sure that eddy kinetic energy is calculated on the same spatial and time grids in both reanalysis and the models. So when we increase the number of models used, and also when we do a like-for-like comparison, the CMIP6 rank increases to 12%, which suggests that a discrepancy is likely. And in contrast, for the AMIP6 models, the rank increases to 29%, suggesting a discrepancy. is unlikely. So the overall results suggest that after all these processes, CMIP6 models could be in error. And looking at the spatial pattern of the storminess trends help us better understand what's underlying the discrepancy. So the figure here shows the spatial map of the trends in Southern Hemisphere storminess. And in reanalysis, we see a strengthening of EKE across all longitudes in the Southern Hemisphere. However, the strengthening is much weaker in the CMIP6 models, and there is almost no trend in the South Pacific. And this is in contrast to the AMIP6 simulations, which have a significant trend in the South Pacific. So more quantitatively, the average rank is 14% in the South Pacific, suggesting that a discrepancy is likely. And in the South Pacific, for the AMIP6 simulations, the average rank is 46%, saying that a discrepancy is unlikely. So from the differences between AMIP6 and CMIP6, we can say that the well-known SST trend discrepancies is impacting the storminess trend discrepancy. So we will move on to the next steps, which are to first quantify the role of internal variability and use model experiments to test our hypothesis that SST trend discrepancy is impacting the storminess trend discrepancy. So to that, we will use the CSM2 large ensemble and pacemaker simulations. So first, to quantify the impact of internal variability, we examine the trends in the 50-member CSM2 large ensemble simulations. And the resulting average rank of this coupled CSM2 large ensemble simulations was 19%, still suggesting that a discrepancy is likely. And we compare this to a AMIP counterpart of the CSM2 large ensemble, which is the GOGA simulations, and the average rank was 32%, saying that a discrepancy is unlikely. And similar things are happening over the South Pacific, where the coupled simulations show a likely discrepancy, whereas the uncoupled simulations show that a discrepancy is unlikely. So this tells us two things. First, that internal variability is unlikely to be contributing to the discrepancy. And second, that we can use the CSM2-based pacemaker simulations to test our hypothesis, which was made in more general CMIP6 models. So now we will move on and test our hypothesis. So we can hypothesize that SST trend discrepancy is impacting the storminess. And more specifically, we hypothesized that the SST trend discrepancy in the Southern Ocean is impacting the surface energy flux trends and therefore impacting the zonal mean storminess trends. And also, we hypothesized that tropical Pacific SST trend discrepancy is impacting the Rossby wave teleconnection trends and therefore impacting the storminess trend in the South Pacific, just as they do in El Nino and La Nina years. So we will first quantify the impact of Southern Ocean SST trend discrepancy using the Southern Ocean pacemaker simulation. So in the Southern Ocean pacemaker simulation, as you can see from this figure, this SST trend in the Southern Ocean is captured. So when the coupled models capture the SST trend in the Southern Ocean, we find that the storminess trend discrepancy in the zonal mean becomes unlikely according to our average rank of 28%. So to better understand this and test our hypothesis, we investigated the impact of surface energy flux trends on the storminess. So this can be done by considering storminess as a poleward energy transport, and we can calculate the energy transport implied from surface energy fluxes using this by expressing surface energy flux as a flux form. So when we calculate this F term across reanalysis and CSM2 large ensembles and the Southern Ocean pacemaker simulations, we find that the rank is 0% in the CSM2 large ensembles, and it is 29% in the Southern Ocean pacemaker simulation. So although we can only do this for Era 5 due to data availability, this suggests that as we hypothesize, the Southern Ocean pacemaker simulations have enhanced storminess trends by simulating the surface energy flux trends closer to the reanalysis. However, even when we pacemake the Southern Ocean, the discrepancy in the South Pacific storminess is still likely. So this suggests that non-local SST trend discrepancy is impacting the storminess trend discrepancy in this region. So now we move our focus to the tropical sea surface temperature discrepancy and quantify its impact using the Pacific pacemaker simulations. So, and as you can see in this figure, in the Pacific pacemaker simulations, the SST trend in the tropical Pacific is captured. So when the coupled models capture the tropical Pacific SST trends, the storminess trend discrepancy in the South Pacific becomes unlikely according to our average rank of 42%. And to better understand this and test our hypothesis, we investigated the zonal wind trends in the South Pacific. So the figure here shows the zonal wind trends at 200 hectopascal in colors for reanalysis, Pacific pacemakers, and the CSM2 large ensemble simulation. So in reanalysis and Pacific pacemakers, we can see a clear La Nina-like teleconnection trends, which is characterized by weaker subtropical jet and stronger eddy-driven jet consistent with stronger storminess. And none of this is simulated in the CSM2 large ensemble simulation. So to better quantify this, we can calculate the trends of the subtropical jet for reanalysis and pacemakers in the large ensembles. And we find that there is very likely a discrepancy in the subtropical jet trends in the CSM2 large ensembles, but the discrepancy is unlikely in the Pacific pacemakers as according to an average rank of 42%. So as a final piece, we can think about combining the impacts of these two pacemakers together, and we can do that by creating a synthetic large ensemble by adding the ensemble mean impacts of individual pacemakers to the 50-member CSM2 large ensembles. And this synthetic large ensemble is particularly interesting because it captures the observed SST trends. So when the coupled models capture the SST trends, which I call this synthetic ensemble sum, the storm track discrepancy becomes unlikely in the zonal mean according to an average rank of 34%, and also in the South Pacific according to a rank of 46%, similar to the AMIP type simulations. So yeah, I'd like to conclude by sharing these two takeaway messages. So after accounting for observation uncertainty and increasing model ensemble size and performing like-for-like comparison, we find that there isn't a discrepancy is unlikely in the prescribed SST simulations, and pacemaker simulations confirm our hypothesis that SST trend discrepancy is likely responsible for the storm track trend discrepancy in the coupled simulations. Thank you.
Great. Thank you very much. Thanks to the organizers for putting this on. And thanks also to my co-authors on this work. So I will continue on the theme of Southern Ocean SST change and also add in some work on Antarctic sea ice trends here. So this is something that has been introduced quite well already. But over the satellite area, we've seen some unexpected changes in Southern Ocean SSTs and sea ice. Here I'm showing the SST from 2 different observational products and the inverse of sea ice extent from 3 different NSSIDC observational products. And you can see that these 2 time series are weakly correlated and that we've seen quite strong cooling and sea ice expansion from the late 70s through to about 2015. And then this trend has reversed in more recent years. The figure at the right shows the spatial pattern in the SST trend from NOAA ERSST version 5 over the full time period. And it's worth pointing out that while the observation products agree quite well in the circumpolar average, these spatial patterns can be quite different from one another. As we've already seen, the Southern Ocean cooling, this figure from Rob Will's paper, is rarely captured in CMIP6. Similarly, the Antarctic sea ice area trends, these are the annual mean trends from our initial CMIP6 sea ice evaluation paper. The observed neutral trend over the full time period is rarely captured by CMIP6. This comparison does depend on the time period you use. If we use the expansion period of 79 to 2015, the observations fall outside of the observational range. And so even though this longer period improves the comparison, I still think it's worth better understanding the processes driving the difference in the sea ice expansion period. The difference we see in the Southern Ocean sea surface temperature trends occurs even when models' global mean sea surface temperature trends are reasonable. This is just one ensemble member per CMIP6 models, just to give you a quick sense to show that when these models capture the global mean trend, shown here on the x-axis, the Southern Ocean SST trend on the y-axis is still very rarely captured. The model I'll use is one of these models that does a relatively good job of capturing the historical trend in global mean SST, and that's the NASA GISS E2.1 climate model. This is a resolution climate model. It has an atmospheric component of 2 by 2.5 degrees, an ocean of 1 by 1.25, a quite simple sea ice component with just 2 mass layers, no ice thickness distribution. And like many CMIP6 models, land ice is represented only by a simple 2-layer model, which is topped by snow cover, with the excess mass that doesn't fit into this representation being discharged to the ocean. The results I'll show from the experiments are going to be focused on the period 1990 to 2021. This is due to some constraints in the experimental setup, which I'll explain. But just to point out that over this shorter time period, the model does a better job of matching Southern Ocean SST and sea ice area than over the longer period in the full observational record. But you can see that while the sea ice area is captured within this ensemble, it's very rare that the ensemble can capture a Southern Ocean cooling trend even over this shorter period. So I'm now going to investigate a couple of drivers that have been proposed previously for the cooling and sea ice expansion. The first being changes in atmospheric circulation. As we heard before from Yue, the southern annular mode has strengthened and shifted polewards due to greenhouse gas and ozone depletion. The Amundsen sea low has also deepened, and there's been an influence of the interdecadal Pacific oscillation. And the second main driver that's been discussed are increases in freshwater fluxes. The net mass loss from ice sheets and ice shelves is generally increasing, and this influences the ocean via changes in salinity and stratification, and is something that's not included in CMIP6 models. There's always been also been increases in P minus E, which is something that has been included in CMIP6 models. So in the first step of this two-step set of experiments, we use wind nudging that we apply to nudge this climate model towards the NASA Maroon reanalysis. Wind nudging is a powerful tool that we've used previously to better understand coupled model biases in the CSM1 climate model. And it works by simply adding a term to the model equations to relax the model towards the meridional and zonal winds from reanalysis every time step. And here we applied this globally and at all atmospheric levels. By design, this means that we capture the observed variability in atmospheric indices, such as the southern annular mode, shown here, with red being our nudge simulations and black being the reanalysis. The technique very effectively limits initial condition uncertainty that arises due to the large-scale atmospheric circulation, such that if we start 3 ensemble members from high, medium, and low sea ice conditions, you can see that these converge within a few years, and for the rest of the simulation, they're very highly correlated, suggesting that we only need a very limited number of ensemble members. By comparing a simulation that began the wind nudging in 1990 and one that started in 1980, suggested that we needed about a 10-year spin-up to allow for the adjustment of the onset of the nudging. And because the reanalysis starts in 1980, that means we focus on 1990 to 2021. This shows the Southern Ocean sea surface temperature anomaly, so that's 50 to 65 degrees south in our control historical ensemble in blue, and then our wind nudge experiments in red and the NOAA ERSST observations in black. And so if we consider the trends over 1990 to 2021 compared to the ensemble mean, which is shown in the blue cross, you can see that our 3 ensemble members with nudging have a reduced Southern Ocean sea surface warming. But they don't get us particularly far and not close enough to the observations. So then in our second set of experiments, we also added anomalous meltwater based on observations, and Gavin led a paper showing the results of a free-running ensemble with the same forcing last year. And so while there have been a lot of different freshwater hosing experiments done in the literature, a point of difference with our studies were to apply interannually varying observation-based estimates that we took from a paper by Slater and co-authors. And this data set spans 1990 to 2021. And you can see these interannual amounts here in the blue time series. We spread this uniformly around the Antarctic coast within this blue mask to mimic the impact of icebergs. And we apply this from 0 to 200 meters depth in the ocean. So then the impact of doing that together with the wind nudging is shown as the orange lines. And you can see these have a very similar variability to the wind nudged experiments. But when we look at the trends, shown here as the orange circles, you can see this has further reduced the Southern Ocean trend to be neutral over this period in one ensemble member and cooling in the other ensemble member. And so if we just compute the difference between the ensemble mean and then the mean of each small ensemble here, we find that adding the winds causes approximately 0.04 Kelvin per decade of cooling, and then adding the meltwater on top of that causes an additional 0.04 Kelvin per decade of cooling, highlighting that both factors are important. However, there are a couple of caveats to mention. Firstly, if we look at the spatial patterns, here I'm showing the SST trend in the mean of the 20 control member ensemble at the left, and then the wind and meltwater mean at the right. The wind nudged alone simulations look very similar to this in terms of the pattern, so this is really being driven by the winds. Now, the reanalyses are quite uncertain in terms of the spatial pattern. You can see that the NOAA SST is much more coherent than had SST4. But even with this difference, the pattern in the wind and meltwater simulation doesn't appear to be quite as strong in the Pacific sector as it should be. We wondered if this might be due to the fact that we had applied our meltwater uniformly around the coast. So in an additional experiment, we tried mimicking this observational breakdown of 70% in the West Antarctic region, with 15% in the East Antarctic and 15% in the peninsula. And this third plot shows that simulation. So this gives us slightly more cooling in the Pacific compared to our previous ensemble members, but it was not really a very large impact. And then the story was a bit more complicated for sea ice. Here are the sea ice area time series. You can see that the nudge simulations do a really good job of picking up the interannual variability in sea ice seen in observations, at least up until about 2016, where they failed to capture this drop. But as the ensemble already did a relatively good job of capturing the neutral sea ice trends over this quite short time period, the impact of the wind nudging has been to give us too much sea ice expansion, which is partly due to this mismatch after 2015, but even in the earlier period, you can see the trend is too strong. And then adding the meltwater on top of that further enhances the sea ice expansion. So finally, just a couple more things to note. In terms of the meltwater experiments, a few caveats here that while we've tried to use these observation-based estimates, there is still uncertainty in observations, especially related to ice shelf melt. These only cover quite a limited time period, which really limited the length of our experiments. And then previous work by other authors has shown that the addition of meltwater can have different impacts at different spatial resolutions, and if the vertical depth of the meltwater, where that's added into the climate model is changed, can also have an impact. As Gavin highlighted earlier, it's clearly a missing process in CMIP6, and it remains to be seen what will happen in CMIP7. The SOFIA MIP is doing an intercomparison of different freshwater experiments across models, and many modeling groups are working towards having fully coupled interactive ice sheets for CMIP7. In terms of the winds, as has previously been discussed already quite a bit today, there are obviously uncertainties in the reanalysis, particularly at high latitudes. We were constrained to use the NASA MERA-2 reanalysis because our model top is high and it's actually higher than error 5. But ideally, we'd be able to test the impact of different reanalyses on these types of experiments. And then in terms of interpreting these wind nudge simulations what exactly we're doing here, I just show on the right a figure where we revisited the experiments that we did with CSM1, because we had also done with this model a comparison between nudging the model towards the full wind field versus nudging the model towards the reanalysis anomalies. That is to say, making this artificial target that's the sum of the model mean climatology and the reanalysis anomalies. And so when we do that, you can see that while the CSM1 and the GIS nudging to the full wind field results are quite similar, these are differences from the ensemble mean in the Southern Ocean SST trend, the anomaly nudging simulations have less of an impact, suggesting that much of the change in the Southern Ocean sea surface temperature that we're seeing is arising from changes in mean winds, which may be suggestive of model biases. To summarize, CMIP6 models rarely capture the observed Southern Ocean sea surface temperature trends, even when global mean SST trends are reasonable. We nudge winds observations and add estimates of observed freshwater from ice sheet and ice shelf melt in a coupled climate model. When we do this, we find that Southern Ocean sea surface temperature trends and variability better match observations, with both factors, both winds and meltwater, being important. But we find that the constrained model simulates too strong Antarctic sea ice expansion and only partially captures the recent sea ice lows. So there's certainly more to investigate here, and especially much more to understand about the recent Antarctic sea ice variability. Thanks for your time.
Cool. Hi, I'm Liz Maroon, coming from University of Wisconsin-Madison. Thanks first to the organizers for the opportunity to speak today. And also a big thank you to my co-authors, Steve Yeager, who might be in the room or might be up. Hi, Steve. As well as grad student working with me, Tadra Lowe. This is very much a team project, and I've got some figures from both of them. But everything that I missay or extrapolate wildly, you should attribute to me, not to them. Also, thank you to NOAA for funding this project. So what's going to happen let's talk about the ocean. What's going to happen in Atlantic Ocean circulation is of great interest to scientists and society. So for example, every 6 months, you can set your watch. There will be a big paper on the AMOC that will give you international headlines such as Atlantic Ocean circulation nearing devastating tipping point. Melting ice could create chaos in US weather. Critical Atlantic Ocean's current system is showing early signs of collapse. Every 6 months, set your watch. And yet, at the same time, our certainty in what we know about what's going on in the North Atlantic has decreased. So for example, in this most latest IPCC report, they've written, for the 20th century, there is low confidence in reconstructed and modeled AMOC changes, Atlantic perennial overturning circulation, because of their low agreement in quantitative trends. Since AR5, this confidence has decreased to new observations and model disagreement. For example, one of those new observations that I think very much influenced this statement was from the overturning in the subpolar North Atlantic OSNAP program, which found that you have a lot more transport coming in from the east side of Greenland from the west side, whereas pretty much all of the models show you have more on the Labrador Sea side, which is a big discrepancy. So that was probably on these authors' minds. And models still widely disagree on what's going on in the North Atlantic Ocean, which is some of what I'm going to show you today. And in particular, something I want to highlight is that since CMIP1, whatever we call that, there's large North Atlantic Ocean, upper ocean temperature and salinity biases, and that these come from the ocean models. These are not a coupled model features. So we really, if we want to figure out what's going on with the AMOC, we need to understand what's going on with these biases, and we need to figure out why they're coming from the ocean models. So this is part of a project that Steve and I are working on with Tadra, and it's got 3 parts, some of which I will tell you about today. The first part is very much software development. How do we develop process-oriented diagnostics for the subtropical to subpolar North Atlantic Ocean that are going to work across different models? And so doing this in a model agnostic way is not trivial. So we've actually spent quite a bit of time working on this. And then on points 2 and 3, I will tell you a little bit new preliminary work. So we're characterizing biases in the upper ocean fields, as well as for thermohaline processes. And I'm going to be showing these today for ocean model intercomparison project simulations. And then the most interesting part, which we're still working on, is identifying relationships between upper ocean model biases and other process-oriented metrics such as water mass transformation and the AMOC itself. If we want to understand trends, we need to understand the relationships in the mean state too. So we've taught the ocean model and comparison project may be of less familiarity in this crowd, since I've heard the word AMOP thrown out, but not OMIP yet. So we're using the OMIP interannual forcing simulations. So interannual forcing simulations use a driving data set. There's one of two part of the protocol, and a driving data set is basically a reanalysis that's been adjusted for driving ocean models. The first one is the core data set, Large and Yeager 2009. And this runs from 1948 to 2009, where you do 5 cycles. So you force the ocean and sea ice model 5 cycles in a row, and you go from 1948 to 2009, go back, do that 5 times so that you give the ocean some time to adjust. OMIP2 protocol is using the JRI55DO forcing as the forcing for the ocean sea ice model. This has a slightly different time period, 1958 to 2018. And there's 5 or 6 cycles in some of these simulations. So we are taking out the atmosphere here and replacing it with reanalysis and seeing just what's going on only in the ocean models. So let's first set the stage. Just what does Atlantic marine olive returning circulation look like in the OMIP simulations, and what are a couple of consequences for what we have in this mean state? So there's a wide range of AMOC strengths in OMIP. This is overturning circulation in density coordinates. Density coordinates are a more natural way of thinking about ocean circulation, since when you're not transforming, you're flowing along isopycnals. We're also using this because it will tie in nicely to Tadra Lowe's work using water mass transformation, which allows us to get a more process-oriented view of what's going on. So how do you interpret this? I've got no little mouse. Oh, I don't have, do I have a mouse? No. It's very slow. Okay, so red indicates clockwise circulation. So, oh, something just changed. Oh, thank you. Great. Okay, so clockwise circulation. So here's latitude on the x-axis, density going from low to high on the y-axis. You've got up here the low density classes. These are subtropical cells. So going this way, here's your equatorial upwelling, and here's the other subtropical cell in that lightish blue color. The AMOC that we've been talking about is actually just all squinched down here. So this is the upper cell of the overturning, where you have your deep southward flow occurring down here around 36, 37 kilograms per meter cube. So these are each one of the OMIP1 simulations. You can see there's a pretty wide variety in AMOC strengths. So oftentimes we're using the max stream function as a metric for AMOC strength. And you can see you have everything from, maybe in the subpolar North Atlantic over here, maybe 12 sear drips to in excess of 20 sear drips. That's huge. Almost 100% difference. OMIP2 is a little bit better. These are the simulations I've got processed so far for OMIP2. There's fewer of them, but there still is a pretty wide spread. So you have some pretty strong ones over here, weaker. Let's look at that in terms of a time series so you can see it a little bit more clearly. OMIP1 on the left, OMIP2 on the right. We are going to confront this with some observations. So in black, I've got the rapid time series. This is what we could think of as like a gold standard for AMOC time series. It's the only long in situ record of overturning circulation, and it's occurring at 26 north. I have smoothed both models and observations using the same processes. What you can see right away is, especially for OMIP1, there's a huge range in overturning strength at 26 north. Rapid kind of has fallen in the middle of them for OMIP1. You're also looking at the rapid, and you can see it has a lot more interannual variability than most of the models there. The OMIP2 range is a bit better. That could also be because maybe I haven't been able to get through the bugs for some of the other OMIP2 simulations that might have a higher one, but for now, this is what we have. Rapid falls a bit more in there, but the interannual variability still isn't the best. So let's, now that we've got this data set, let's start thinking about what are the consequences that we have for this. So here we've got climatological AMOC strength at 26 on the x-axis versus standard deviation. On that last plot, you might have said, hey, looks like some of those lines that have greatest multi-decadal variability also are the strongest AMOCs. And you did pat yourself on the back. You're quicker than I am. So here we have a relationship. There's a weak relationship between AMOC mean strength and how much variability there is in the AMOC in each model. Triangles are OMIP2, stars are OMIP1, and I'm using all 5 cycles of the OMIP simulations to just get a sense of, for any of these, what kind of adjustment is there over the 5 cycles. So that's one relationship. We can see that AMOC is associated with greater variability, and then there's the black rapids in the middle. Here's where we're confronting a trend. Models with stronger AMOC also show greater decline since 2000. A lot of that variability is actually the decline. So here we got, again, AMOC on the x-axis, mean strength, and the trend since 2000. I'll just, the OMIP1 simulations stop at 2009, whereas the OMIP2 ones stop at 2018. So these trends are calculated over slightly different time periods, so do take that into account. But you can see that there's also this relationship. Stronger AMOC is associated with greater decline. And this is also something that's been widely seen in the projections going back multiple CMIPs. Stronger AMOCs have greater declines in the 21st century. I think Giada Serato just had a nice poster that touches on this and some of the implications. So I think the point I'm trying to make here is that if we want to understand trends in AMOC strength, which is really important for the climate system, we really need to get a hold of why is there multi-model spread in the AMOC mean strength. If you want to get the trends and the variability right, we have to figure that out. So what I'm going to do for the rest of the talk is think about one area that might have relationship to AMOC mean strength, which is biases in the North Atlantic Ocean. So this is a figure from Steve, and this is the bias of the climatological temperature field in the OMIP1 simulations relative to EN4, which I've got down here on the left. We have boxed the region that has that big bullseye of blue. So these are biases in excess of 5-6 degrees in every single OMIP1 simulation. This is not a new result. This goes back to CMIP1. This blue spot of death, which is what Anand got. I did not coin that wonderful term. It's from Anand Desikan's paper in 2007, the blue spot of death. And the reason why it's there is because 1 degree ocean models really don't have a good handle on the North Atlantic current. The current's too diffuse, and admit they all miss the bends and meanders that are in the climatological North Atlantic current. In particular, there's like a northward bend kind of like directly south of Greenland they miss. And as a result of that, the boundary between warm, salty, subtropical water and cold, fresh water gets totally missed. So you can think of this as the subtropics are too big and the subpolar regions, the other way around, subpolar regions too big. So you're getting those cold biases further south. So still a problem in today's models. And these are ocean sea ice only models. This is not coming from the atmosphere. These are forced by historical atmospheric fields. OMIP2 has the same problem. I'll just move quickly by that. And then again, this is because the currents are wrong. So salinity biases also go along with these issues. So this is now the same North Atlantic current region box. You've got very fresh bias that goes along with that cold. So cold and fresh biases go together, warm and salty go together. And then OMIP2, again, same issue. So here's another figure from Steve that shows this relationship, temperature bias on the x-axis, salinity bias on the y-axis, OMIP1 on the left, OMIP2 on the right. Particularly in OMIP1, you see a strong relationship between these two biases. OMIP2, it's less so, there's a less spread, so that maybe that indicates improvement using that forcing data sets. That's something we should dig into. So now to get back to what are the consequences for the AMOC of these biases? I'll first say that it's very hard to disentangle what is causing what up here, because the AMOC has advection, which can affect temperature, but temperature also is part of the thermohaline circulation, which forces the AMOC. So I'm not going to argue any direction of causality here, only say that we do have these relationships. On the x-axis, we have AMOC at 45, and at the y-axis, we got temperature bias. There is a weak relationship, Stronger AMOCs have greater temperature bias. And then the same goes along with salinity. And you tend to have a greater fresh bias in the models that have climatological strong AMOC. And so you're thinking, okay, temperature and salinity, those are going to work together with a thermohaline circulation. So if you combine those two to look at the density bias in that North Atlantic current region versus AMOC strength, there is no clear relationship. It's with the mean AMOC strength. Maybe this means that the AMOC is driving the biases themselves rather than the biases driving the AMOC, or maybe there's something else we need to understand. I don't fully get this yet, and we're going to be looking into this, but I think it's quite interesting that while you do have a relationship with temperature and salinity, you don't with density. So finally, now that we've got this nice data set of AMOC and sigma space and temperature and salinity work together, we can start doing some really cool stuff, including cross-model correlation. So I'm using all of the OMIP simulations here to figure out how they're related to that temperature bias in that North Atlantic current region. So the contours are the multi-model mean AMOC stream function, and the shading only shows statistically significant cross-model correlation coefficient. So the things I want to point your attention to are, let's start with this orange zone here. So this is just north of that temperature bias zone. What this indicates is that when you have a reduced cold bias, you have stronger stream function in these regions, which means that you're having northward flow occurring at lighter densities. And that should make sense. If you have less cold bias, you're automatically going to be at hopefully a lesser density. So this sort of makes sense. This says that the temperature bias is probably causing flow at lighter classes. More interestingly is this big purple zone. This is the main AMOC stream function, so flowing around like this. What this indicates is that when you have reduced cold bias, you also have a weaker AMOC. And it occurs at the southward return flow occurs at slightly lighter classes. So let's look at this in another way. I've taken the three models that have the weakest cold bias on the left. Again, the contours are multi-model mean, and then the shading is those three models. And on the right, we have the three strongest cold biases. So you can see that a little better. You see that the stream function is a little stronger up in this zone at lighter classes and weaker AMOC overall. And you have a stronger AMOC with transformation occurring down here at slightly denser classes. So really, what's next is water mass transformation, because that will allow us to start figuring out how these temperature biases are affecting the AMOC. Is it through the surface field itself? Is it through how the surface heat fluxes are impacted by temperature biases? So stay tuned. This is work that the grad student, Lettie Roach, she's working on with me. She's been putting together observation-based estimates of water mass transformation, some of which I've got here, which gives us a pretty good first order estimate of AMOC itself. So in the interest of time, I will just leave my summary up here. And again, thank the organizers and all of you.
And it seems it is the global notching, the wind, and which region of wind, which region is important for making southern ocean cooling? When we see the weird lizard, it seems that southern hemisphere, extratropical southern hemisphere's wind does not matter that much for the southern ocean cooling. So in your wind nudging experiment, maybe the tropical wind matters because they can make the linear cooling and they can make the direct connection to the southern ocean. So do you have any opinion which region's wind is important?
Yeah, so the experiments I showed in the talk were with global wind nudging, but we also compared to experiments that we'd done previously with CSM1. And in those experiments, we nudged the winds polewards of 45 degrees. We did both hemispheres together. We also did one hemisphere at a time. And obviously there are differences between the models, but it seems like the impact is broadly similar between the two. So I would suggest that suggesting that it's mostly southern hemisphere forced.
Could we do the question online? Could you read it out? Maybe I'll try to get it up.
The question is from Kate for Joonsuk. She really likes the clear methodology of the ranking, but wonders about can be equal weight to all reanalyses. This comes back to Gavin's earlier comment about structural uncertainty. And ideally, we would have a large ensemble of observational estimates to work with. She says, for my part, as an observational stand, I'm sorry I haven't managed to do that with my own data sets yet. So I think the question is, I guess I have a kind of an add-on. It's like, yeah, how much do we trust all of the reanalyses, and can we kind of narrow them down? And if more certain than others, I guess.
Yeah.
Okay.
Oh, okay. Yeah, I thought actually. Yeah, so I think it's maybe just to rephrase or maybe just summarize something that can make us have more confidence on what reanalysis to trust or not would be a great future work. And just regarding the Southern Hemisphere storm tracks, as we had 6 reanalysis data sets and we investigated the temperature trends, and there were no obvious connection to the temperature from the temperature trends to the reanalysis storm track trends, which can infer choice of reanalysis. So yeah, one thing clearly I can say is NCEP had a bias in its climatology, so maybe we could consider removing that from the reanalysis ensemble. But other than that, as of now, we couldn't find a solid conclusion to that.
So Clara's hand first.
I have a question for Lettie. Can you comment at all about the seasonal dependence or seasonality of both the SST, Southern Ocean SST trends, the sea ice trends, and wind forcing trends? I'm trying to get a good picture in my head of how that plays into the annual trend maps.
Yeah, I guess I have to confess that most of our analysis has been with annual means. Certainly for the sea ice trends, I mean, we're seeing we're seeing the trend is not as seasonally dependent as the Arctic. So we've generally seen bigger changes in a relative sense in summer than winter. But yeah, honestly, besides that, I don't have a lot to add yet, but I'm planning some more analysis, and I will be sure to look more in the seasonal dimension.
Alexis?
I have a question to you. So you had a comment about OSNAP West and OSNAP East, particular less importance of overturning through OSNAP West. In OMIP 2, is it really consistent with this idea, or still Labrador Sea and Nordic Sea doesn't really matter? It happens everywhere.
I'm going to defer your question for a few months. I haven't been able to get the lines exactly right to do that decomposition, so I can't tell you the answer. Maybe someone else in the room knows off the top of their head with OMIP simulations. It's not an easy calculation because the OceanMap West is not straight. It's kind of going back and forth and across the Labrador Sea.
Okay, next we'll take one from online from Yu Liang, who has a question for Ray. Does ERA 5 assimilate observed sea level pressure? If so, why doesn't the relationship between stream function and SLP hold in ERA? Does ERA 5 assimilate observed sea level pressure? And if so, why doesn't the relationship between stream function and SLP hold in ERA 5?
Yeah, so there is the relationship between sea level pressure and the stream function, but if there are many processes that could affect the stream function, not just, you can simulate correctly the sea level pressure, but then if other things affect your sea level pressure, then eventually you won't get the correct circulation changes. There is one reanalysis, the 20th century reanalysis, that only assimilates sea level pressure. In that you can get the correct circulation. It comes down to your equation of sea level pressure, what affects actually sea level pressure in those points. Yeah, I need to do it.
Guess Karen then?
Yeah, also for Liz, so a theme of this workshop is everything is wrong, right? And so I wonder with the, if you know specifically, and I know you're not probably an observationalist, but for rapid, are we really comparing the right thing in the models to what rapid is measuring? And what are the structural errors? You know, that it's one line, we know that's not right, but you know, do we have a feeling of the structural errors in rapid?
So upstairs, I think that's what Fred Costuccio has been working on with the AMOC metrics project. So rapid is an array where you are a bunch of different components, including cables and moorings. So you're not actually measuring all the way across all the transport. You're measuring at certain spots. So the best way, if you were trying to compare a model with the observations at rapid, would be to use the model at each of the same spots. And that's what Fred's been doing as part of the AMOC metrics project. And I remember a lot of very interesting things coming up, like standing eddies, certain locations where that mooring was, and that were in the models, but not the observations, or vice versa. That definitely affect your interpretation if you were doing like you know, I was taking just across the entire basin AMOC. I mean, I wasn't using moorings, but that would be the better way to do it. But it's, again, not a simple calculation.
I have a question for Joonsuk. So a later part of your talk, you combine this tropical pacemaker grounds and subscription pacemaker grounds, and it got the EKG trends much better close with observations. But since you identify these two regions, tropical with Southern Ocean, and we know these two regional pacemaker ensemble both have a remote impact. Like the Southern Ocean have a remote impact on the tropics, and tropics have teleconnection to the Southern Ocean. When we add them together, wouldn't that result in sort of an overestimated coding that is supposed to be stronger than observation?
Yeah, that's a fair point. And we see teleconnected impact on SST. And I think that's, I think I showed in the figure, and that teleconnection is what makes this, so even you nudge this specific area, as you nudge tropical Pacific, and you nudge Southern Ocean, with that teleconnection impact, you get a full structure of the Southern Hemisphere SST trends outside the nudged areas. So, for example, I think we discussed it earlier in Sarah. This is Sarah's SO-based simulation. So, in that simulation, you don't get like collect connection of Southern Ocean all the way up to the tropical Pacific. You only get it up to like east coast of the South America. So I think that really helps like with SST trends in this application.
Just to follow up on that, I thought you showed that you can kind of add the two up linearly and they look like the other, right?
Yeah.
So that there's not too much. Yeah.
I have a question for Elizabeth. So we've done some work, not with OMIP, but with CIMIP models with Andrea, a PhD student working with me. So we noticed that the models that have a stronger AMOC meaning in future projections also tend to have deep water formation in the Labrador Sea as compared to the model that have a weaker AMOC weakening in the future, that those instead show more deep water formation in the mean climates in east of Greenland. So I was wondering if in your picture of the temperature and salinity biases, maybe could this fit in? Did you look to this or?
We're definitely looking into that. So Tadra has been looking at water mass transformation and dividing things up by where they are occurring. So east of Greenland versus west of Greenland. And when we get to finally getting through all of those OMIP simulations, I'll have a better answer for you of whether you see more deep water formation to the east of Greenland, and whether that does also associate with weaker. So again, stay tuned.
Tim had his hand up first.
Yeah, question for Ray. Really nice overview. This is going to sound very pessimistic, but I was struck by your one kind of green smiley face at the start with the was that the Southern Hemisphere summer trends, which we think obviously have an ozone impact. Do you think we're kind of too trusting of that? Should we be really probing that result to check that we're getting that trend for the right reasons, given how hard it is to get circulation right otherwise?
Yeah, absolutely. We should, in that paper with Dim, we wanted to see why CMIP6 models are better capturing CMIP5. That's what you're asking about, right? And you can eventually tie this to meridian temperature gradients. And you can use actually measurements of temperature in the atmosphere and to try to see whether these fall similar to what we see in CMIP5 or CMIP6. And also, we did this attribution analysis to see where it is coming from. And I talked about biomass burning, and we looked at short wave radiation at the surface. We saw how this took these trends in find CF6 in reanalysis, and CF6 seems to do a better job capturing that trends. This is related to biomass burning emissions. I can show you later the figures, but eventually you want to link that to some observation aside from the storm track metric to ensure that the CF6 are doing it the right.
Rei Chemke. So apart from biases in the reanalysis, how important could be the internal variability to the discrepancy of like a Hadley circulation?
Can you speak louder?
Yeah, so apart from biases in the reanalysis, how important do you think the internal variability to the Hadley circulation strength trend? Because I believe there are some papers which mention the influence of AMO phase changes to the recent Hadley circulation trend.
So you mean importance for what? For the model?
Comparing with the biases in the reanalysis.
So, you know, the internal variability affects the analysis also in reanalysis. So the problem is that the reanalysis eventually do not agree with observation for measurements of sea level pressure. So, you know, it could be that internal variability is what biased in the reanalysis. And with my work in Lorenzo, what we found is actually there are biases in latent heating in the deep tropics in the reanalysis. It's actually causing that. So I think this is more realistic direction than internal.
Questions?
To Ray, smiley face. I wonder though, is there a distinction to be made between the coupled models and the AMIP? How much of what we're seeing is coupling, which seems to be a very important other comparisons?
Yeah, that's a good question. So for some, I think people try to, for example, the BlackRock 5 paper about the North Atlantic gesture, they look at it. For some, I think people try to look at it, and others not. It's a good point. We can use, this is part of what we say, I said that we need to use numerical, targeted numerical simulation, try to understand where this is coming from, and AMIP is this kind of theory.
In particular with the Hadley cell. I mean, Walker cell we saw this morning, strengthening an AMIP, weakening CMIP. You know, for the Hadley cell,
Strength or the width?
any, I'll take anything.
So for the width, I think Kevin, I don't think you can comment on the width.
Yeah, I mean, it's better in the northern hemisphere in AMIP for sure. In the southern hemisphere, like there's not a lot of difference between the fully coupled and AMIP, but in the northern hemisphere, the recent PDO trend has made a big impact in terms of the Hadley cell trend. I don't know about strength, right? You would know more about that probably.
I remember Lorenzo that look. It's worth checking.
So this is a question for Lettie, but anyone also. So I wonder what the role of the resolution of the ocean in representing the Southern Ocean SST trends would be, both horizontally and vertically.
Yeah, I mean, I think that's a really important point and something that, I mean, I was actually quite surprised with this model that we could capture things as well as we could, given that it is quite low resolution, but I definitely expect, I mean, certainly there's papers that have shown that the freshwater response varies with resolution as you go to higher resolution are better able to resolve the slope currents, that you can kind of better trap the fresh water on the shelf, giving a different response to lower resolution models. But yeah, I guess hopefully with high res MIP and stuff coming out, as more modeling centers are doing higher resolution runs, we'll see more.
So the atmospheric reanalyses may be bad, but I know, are the ocean reanalyses ugly, Liz? Is there any way that we could use ocean reanalysis to start to assess trends?
I thought about that actually in preparing for this talk. I was looking back towards the ocean reanalyses, their estimates for AMOC. So Alicia Karspek's got the paper that goes all the way back to the 1950s. And my recollection of that one is it's just awful. If you're looking at AMOC, I can only really speak to that one thing. Since the satellite altimetry era, so like 1993 onward, Laura Jackson's done the comparison on those. There's a lot better variability. But in her paper, I was noticing that she takes out the mean AMOC and all the reanalyses and just sticks them all centered on 0 as anomalies. So I was actually thinking, should I spend a good week of my time right before this going back and calculating AMOC for all the reanalyses, the ocean reanalyses, to see how much they, where do they actually sit in mean strength space? And I decided against it because I only have so much time. But yeah, I think that's another tool we can use. I don't think it is going to be as trustworthy as RAPID or OSNAP, but I definitely think we should incorporate it as much as we can.
I think there are products directly from RAPID and also may combine satellite and also are big products can be used to be compared with. Yeah, I agree.
So we would have time for another question if there is one, but yeah, go ahead.
I have a question for Ray. So, broadly speaking, we have all these like orange and red bases. I wonder, I mean, you probably did the Gaussian analysis in a zonal sense. I wonder if we can attribute these biases or disagreements to some regional processes, say monsoons being a big part of health circulation, etc.
Yeah, absolutely. I think this is a good next step to do, to look at more region.
Working together.
Sure. Any last questions? Are there announcements? We're going to make that break sessions.